Hello there, and welcome to Science for Sleep, where the vastness of the universe turns into a quiet companion and the most daunting questions become something you can simply rest beside. Tonight, we're drifting toward one of the strangest places ever imagined, a place where the rules we know break apart, where gravity becomes so overwhelming that even light can't find a way out, and where time itself begins to behave in ways that feel almost impossible. It's called the Singularity, the point at which the universe, as we understand it, seems to run out of instructions. But before we dive into that, I wonder where you're listening from. Maybe you're in a dark room with nothing but the soft glow of your screen, or perhaps you're lying in bed while the world outside is quiet and still. And if you are, I'd like to ask you a small question. Do you ever think about how far away the edge of everything really is? Because tonight, we'll take our time wandering toward it, gently, one idea at a time. If you find this soothing, or if this quiet trip through the cosmos helps you slow down, I'd be grateful if you gave this a like or even subscribed. It helps keep this calm corner alive for anyone else who might need a soft escape from the noise. Now let's begin, not with an explosion of facts or a storm of equations, but with something much simpler. A moment to sit with the strange thought that there are places in the universe where our best understanding of reality simply stops. Imagine that for a second. You're standing on a familiar shore and you see the ocean stretching out in front of you. You know what water is. You know how waves behave. You've seen tides come in and out your whole life. But then, just beyond the horizon, there's a line you're told you can never cross. And past it, everything you know changes into something unrecognizable. That's what a singularity is. It's not just a point in space. It's a boundary where the universe shrugs at our knowledge and says no further. The most famous singularities sit inside black holes, but the idea reaches even further than that, to the beginning of the universe itself. Because according to our best models, there was a moment before there were stars, before galaxies, even before space had room to stretch, when everything was compressed into something smaller than anything we can picture. A single point with infinite density and no size at all. That's the kind of description that doesn't sit comfortably in the mind. It isn't meant to, because it isn't something we're built to imagine, yet we keep trying. Because even if we can't see a singularity, we can feel the pull of its mystery. Think about gravity for a moment. Not the quiet pull that keeps your feet on the ground or holds the moon in orbit, but gravity turned up so high that it stops being a background force and becomes the only thing that matters. When a star burns through all of its fuel and collapses in on itself, its core is crushed smaller and smaller until even the atoms can't hold themselves together. What's left is an object so dense that nothing, not even light, can escape its pull. If you got too close, you wouldn't be able to turn back, because the escape velocity, the speed you'd need to run away, would be faster than light. And nothing in the universe can move faster than light. That's the point where a black hole forms, and deep inside it, past the invisible surface we call the event horizon, is the singularity, the ultimate destination, where everything that falls in is drawn down to something we can't describe. But before we go any deeper, there's something comforting in knowing that this isn't a story about falling. It's a story about looking from a safe distance. Because singularities, while terrifying in theory, are far away, tucked neatly inside their cosmic prisons. The closest one we know of is thousands of light years from here, so there's no need to hold your breath. This is not a tale of danger. It's a chance to stand very far away and simply watch, while the universe does something so extreme it almost feels like a trick. One of the oddest things about singularities is that they don't sit there in isolation, like exotic cosmic artifacts. Most galaxies, including our own, seem to have one hiding in the middle, quietly anchoring the stars that spin around it. Our own Milky Way has a supermassive black hole at its heart called Sagittarius A. It's millions of times heavier than the Sun, and yet it's invisible. We only know it's there because of the way nearby stars whip around as if they're dancing around a partner they can't see. What that means is that singularities aren't rare. They're woven into the structure of the universe. They're not a glitch, they're part of the blueprint. And if you follow their story long enough, they even lead us backward in time, toward the very first singularity, the one that may have birthed everything. And that's where things get even stranger. Because if we rewind the universe all the way back, every galaxy, every star, every atom, every photon of light, we eventually arrive at a moment where there's no room left to rewind. Everything is crushed into one incomprehensible point, a cosmic singularity that marks the beginning of time itself. And yet, if we ask what came before that, we find no answer. Not because no one has thought of one, but because the question might not even make sense in the first place. Time as we know it may not have existed at all. Before that singularity, there was no ticking clock, no before to compare to any after. Just that impossible point, waiting to expand. This is where our journey tonight really begins, not with certainty, but with the quiet acceptance that singularities are places where knowledge meets a wall. And instead of turning back, we sit there for a while and look at the wall itself. We know that general relativity, the great theory that explains how gravity works, does a remarkable job of describing everything right up to the edge of a singularity. But the moment we try to peek inside, those equations stop giving sensible answers. They break down into infinities, meaningless numbers that don't fit with reality. And in that silence, in that gap between what we know and what we don't, is the reason singularities keep us awake, not with fear, but with fascination. Yet even if we can't see them directly, we can watch what they do to everything around them. And that's what draws astronomers to their study. Because while the singularity itself is hidden behind the event horizon, its presence shapes space and time in ways we can measure. Stars orbiting in tight loops at impossible speeds, gas clouds heated until they glow in X-rays, jets of matter thrown out for thousands of light years like cosmic searchlights. Every one of those signs is a footprint, and each footprint leads back to the same invisible point. And maybe there's something strangely comforting about that, because even at the edge of understanding, we still find patterns. The universe doesn't give us every answer, but it doesn't abandon us entirely. It leaves a trail, like breadcrumbs leading into the dark, and we follow them, not because we expect the path to end, but because every step feels like standing closer to a truth that's been there since the beginning. So if you're still with me, listening as the world outside grows quieter, imagine for a moment what it's like to be near one of these cosmic abysses. Not falling in, not even approaching the event horizon, just sitting at a safe distance while space itself bends around it. Stars curve along strange paths, and time begins to run just a little differently from the way it does here. Maybe you can even feel it, the sense that, out there, the universe is holding secrets so tightly they might never be pried open. But still they're there, pulling at us softly, like gravity itself. And that's where we'll keep going. Because from here, the story doesn't end. It only deepens. Singularities are not just points of no return. They are quiet reminders that for every answer we find, the universe still has a way of placing one more question just ahead of us, waiting, like a faint light in the distance. There is something undeniably captivating about the idea of a singularity, but perhaps what draws us in the most isn't the science or the incredible forces at play, but rather the deep and ever-present question it presents. How can something exist without rules? A point in space that defies everything we know, yet still behaves as though it has its own set of instructions, pulling in everything that comes too close with an intensity we can only begin to fathom. That's the true allure of the singularity. It is not just a place, it is a question, one that pulls at the very fabric of our curiosity and invites us to step closer, even though we know we cannot truly understand it. Perhaps it's because this question stretches beyond the bounds of physics and into the realm of philosophy. When faced with a singularity, you're forced to confront not just what we know, but what we can never know. It's like looking at a locked door, knowing that behind it lies something incomprehensible, yet feeling an overwhelming need to find the key. The singularity isn't just a place where the universe ends. It's where the known and the unknown meet, and the vast gap between them becomes undeniable. This paradox, this tension between what we can grasp and what we cannot, is what has intrigued humanity for centuries. It wasn't always black holes or singularities that captured our attention. In ancient times, we would have looked at the stars and asked similar questions, gazing into the night sky, wondering what it all meant. What was out there? Why do we exist at all? But now our eyes are focused on something a little closer, a point in space so dense, so compact, it warps the very fabric of space and time. If we were to follow the trail of questions, it would take us all the way back to the very first ones posed by the early astronomers and philosophers. Why is there something rather than nothing, they might have asked? The singularity, in its infinite density, gives weight to that question. Because as we will see, the very concept of the singularity challenges our understanding of beginnings and endings, space and time. It's not just an academic pursuit, it's a question that shakes the core of how we understand the universe. Imagine, for a moment, standing on the edge of a precipice. You cannot see over the side, and all you feel is the strange tension between what's behind you, the safety of everything you know, and what's ahead, where nothing is clear. You might hesitate, caught between the two. The singularity is a bit like that precipice. It draws you in, but with it comes the uncertainty. We know, of course, that we can never truly cross the event horizon of a black hole. The point of no return is called that for a reason. Yet something in us remains fascinated. The question remains, what lies on the other side? We have observed black holes, studied their effects, and theorized about their interiors, and yet, the question of what actually happens at the singularity itself remains unanswered. We know that the forces are unimaginable, that time slows down near it, but what happens inside? Does everything collapse into a single point, or is there something else, something we can't quite see, waiting to be discovered? There is no escape from the pull of this question, not for scientists, philosophers, or anyone else who dares to think about the unknown. The singularity holds its mystery so tightly that it mocks our attempts to fully understand it. The more we learn, the more we realize how little we truly know. The closer we get, the more we have to let go of our previous assumptions. This question also points to something very fundamental about how we approach knowledge. It's easy to get comfortable with the answers we think we have. It's easy to believe that if we simply look at something long enough, we will understand it. But singularities challenge that. They are reminders that there are limits to what we can grasp, no matter how advanced our tools or our minds become. And yet we cannot stop trying to answer the question, even if the answer may forever elude us. This is the essence of human curiosity. It isn't the certainty of answers that drives us. It's the pull of the questions themselves. They keep us moving forward, even when the path ahead is unclear. And as long as the singularity exists, as long as it pulls at the very fabric of our understanding, that question will remain with us. What lies beyond the event horizon? What is the nature of a point so dense that nothing can escape it? When we look at the cosmos, we're often struck by the vastness of it all. Galaxies spiral out of control, stars burn out, and nebulae form and collapse in a cosmic dance that has been unfolding for billions of years. But the singularity stands as a sort of final frontier, a place where the forces of nature push against each other with such intensity that even the universe itself can barely comprehend what's going on. It is both the ultimate mystery and the final answer to the question. What happens when the laws of physics break down? The question pulls at our imaginations, urging us to dream up new theories, to test our understanding of space and time. It challenges us to think beyond the known and to confront the possibility that the universe might be far stranger than we can ever fully understand. It's humbling in a way, because it reminds us that there will always be things beyond our comprehension. And yet, that very mystery is what makes the universe so endlessly fascinating. Every discovery we make only opens the door to more questions, and as long as the singularity remains one of the universe's most perplexing phenomena, those questions will continue to echo through our thoughts, pulling us ever closer to the unknown. In fact, the more we study the singularity, the more we realize that it isn't just a place, it's a reflection of everything we don't know. It's a reminder that our understanding of the universe is still in its infancy. The idea of a singularity, a place where gravity is so intense and time so warped that everything collapses into a point of infinite density, is as much a symbol of our limits as it is a physical reality. It's the universe's way of saying, here, you can go no further. But even though we can't cross the event horizon or reach the singularity itself, the question that the singularity asks is one we can't escape. We feel its pull every time we look up at the night sky, every time we wonder what's beyond the stars, and every time we ponder the mysteries of time and space. In the quiet, as we reflect on what we know and what we don't, the singularity stands as a reminder of how much we still have to discover. And so, we press on, not because we expect to answer the question, but because the question itself is what drives us forward. It draws us toward the edge of the unknown, and in doing so, it invites us to explore not just the universe, but the limits of our own understanding. So as you lie there tonight, wherever you are, and think about the universe, know that the question remains, what is on the other side of the singularity? The answer may never be fully ours to grasp, but the search, the journey to understand, is what makes us human. There are few concepts in the universe more confounding than the singularity. It's not just the idea of an object or a force, it's the very nature of a singularity that throws everything we understand into question. Imagine a place that exists in every corner of the universe, yet cannot be seen, touched, or even properly imagined. A place with no size, no edges, no beginning or end. It's a place that exists at the heart of black holes, yet exists in no specific location at all. It's as though you were trying to navigate to a place that doesn't even have a map, let alone any physical reference points to guide you. What does it mean to talk about a point with no size? It seems paradoxical, doesn't it? In our everyday experience, we are surrounded by objects with measurable sizes. We can touch them, walk around them, and even build things around them. Everything we know is contained within boundaries, within limits we can see, calculate, and feel. But the singularity is a different beast entirely. It's not an object or a place in the traditional sense. It is a point in space where matter becomes so compressed that its volume is essentially zero. The density, on the other hand, is infinite. We might say that the singularity is a point, but this word doesn't truly capture the essence of what it represents. We use it because it's the closest analogy we have, but the word itself is a poor stand-in for something so unfathomable. A point is something we can imagine as a place, something we can mark on a map, but the singularity is not like that at all. It's not on a map. It isn't something we can pinpoint in space. It's beyond the limits of what we can conceive. And yet, we know it's out there, lurking in the heart of every black hole. At the very core of a black hole, there exists an infinitely dense point where gravity overwhelms everything, where the mass of the black hole is compressed into an incredibly small area. The very idea that space itself can be distorted to such a degree that it folds in on itself is hard to grasp. There is no space left, no room to measure. Imagine taking all the mass of a star, compressing it so tightly that it no longer takes up any space at all. What remains is the singularity, the ultimate limit of matter and energy. It's the ultimate collapse, where everything we know about the world stops making sense. Now, try to picture what that would look like. We can't, really. We might imagine a tiny dot at the centre of a black hole, but it isn't a dot in the traditional sense. It's not something we can see or even conceptualize in terms of regular dimensions. Space itself, the very fabric of the universe, behaves differently near the singularity. Time itself bends and warps. Inside this strange point, everything ceases to obey the rules we've learned to live by. Time stops. Space becomes infinitely stretched, and the fundamental constants of physics as we know them break down. But despite the strange and unimaginable nature of the singularity, there is something fundamentally compelling about it. It's a point in space that pulls at us, even though we can never touch it. It invites us to wonder what happens when the rules of physics no longer apply. And in a sense, it's this very mystery that makes the singularity so intriguing. It's the absence of a map that sparks our imagination. The idea that there is a place in the universe where nothing makes sense, and where everything we've learned might need to be rewritten, is both unsettling and exhilarating. This is the paradox of the singularity. It exists in a space where there are no boundaries, no edges, no points of reference. But even in that vast emptiness, it's a place of ultimate importance. The singularity doesn't conform to the rules of reality that we've come to rely on, and yet it is the reason for many of the cosmic phenomena we observe. Without singularities, there would be no black holes, no stellar collapses, no gravitational lensing, no bending of light. The singularity is not just a theoretical idea, it's a driving force of the universe. It's what makes black holes work the way they do. It's the reason that galaxies form, stars burn, and planets orbit. It's the point where gravity reaches its limit, where the very concept of space and time breaks down, but also where the universe begins its most mysterious dance. To talk about the singularity is to talk about the end of the familiar. It's like standing at the edge of a cliff and looking down, knowing that the ground below you is a long way off, but being unable to see the distance. We can describe the singularity mathematically, but we can't truly picture it. It's a place with no size yet infinite density, a place that doesn't fit into our understanding of the world, and yet it exists in the very fabric of the universe, shaping everything around it. So, why is it so difficult to wrap our minds around this idea? Part of it is that we've never encountered anything like it in our daily lives. Everything we interact with, from the smallest particles to the largest galaxies, follows the basic principles of physics. But the singularity doesn't follow those rules. It's a place where gravity becomes so intense that it warps space and time. It's a place where the very fabric of reality tears apart, where the familiar laws of nature stop functioning in any recognizable way. We cannot touch it, we cannot see it, but we know it's there. And in that knowledge lies a deep, almost primal fascination. One of the key challenges of understanding the singularity is that it represents a point of infinite density. Think about it. The singularity is a place where an unimaginable amount of mass is packed into a space so small that it has no physical dimensions. The gravitational pull is so powerful that not even light can escape. It's not just an object, it's a force that warps the very structure of space and time around it. This infinite density is what makes it so difficult to understand. We simply don't have the language or the tools to describe a place that doesn't follow the basic principles of physics. But while it may be difficult to picture, it's also something that has been observed in action. Astronomers can't see the singularity itself, but they can see the effects it has on its surroundings. Stars swirl around black holes. Gas clouds are stretched and compressed by the immense gravity, and light is bent in strange ways as it passes near the event horizon. These observations give us a glimpse into the behaviour of singularities, even though we can never directly observe them. It's as though we're standing on the shore, watching the waves, but never quite able to dive in. The singularity is a place that exists outside our understanding, a place where the usual rules of reality break down. It's a reminder that there are limits to our knowledge, and yet it is also a reminder of how far we've come in our understanding of the universe. The fact that we can even begin to describe a singularity, even if we can't truly understand it, speaks to the extraordinary nature of human curiosity. The singularity may be a point with no size, a place with no map, but it is also one of the most important and fascinating phenomena in the cosmos. As you lie there, perhaps drifting off to sleep, consider the singularity. It exists in the farthest reaches of space, beyond the event horizon of a black hole, where time and space merge into something completely alien. Yet, even from this distance, it calls to us, pulling us with the question of what it is and how it works. It's a place we can never reach, a point we can never touch, but it is also the key to understanding some of the deepest mysteries of the universe. In the absence of a map, we continue to search, to wonder, and to imagine what lies beyond. When you think about gravity, you might picture a few simple things: an apple falling from a tree, the moon pulling at the oceans to create tides, or the earth itself holding everything down, keeping us firmly planted on the ground. In our everyday experience, gravity is a predictable, reliable force. It's what keeps us anchored, what gives us weight, what allows the planets to orbit the sun. But what happens when gravity gets so strong, so intense, that it stops behaving the way we expect it to? When gravity gets pushed to its limits, when it starts playing unfairly, it doesn't just shape the universe, it warps it completely. Imagine this. Gravity is what holds our world together. It keeps the stars in the sky, the planets in their orbits, the galaxies spinning in perfect harmony. But what if you took all of that mass, all of that gravity, and packed it into a tiny dense space? Suddenly, gravity becomes a force that no longer behaves according to the simple rules we're familiar with. It starts bending and twisting space and time itself, creating something entirely new: the singularity. The singularity at the center of a black hole is where gravity becomes so overwhelming that it begins to overpower everything. We already know that gravity pulls things together: planets, stars, even light. But in a black hole, gravity is so strong that it crushes everything into a singularity, a point of infinite density. It's as though gravity has become a force that is too powerful to be contained by the universe's regular rules. It's no longer just a force of attraction. It's a force that completely warps the very fabric of space and time. The more massive an object is, the stronger its gravitational pull. This is true for everything from tiny asteroids to massive supernova remnants. But when you reach the scale of a black hole, gravity reaches its limit. It pulls everything inward, squeezing matter into an infinitely small point. The larger the mass, the more severe the warping of space-time, until it becomes impossible to escape. That's when you cross the event horizon, the boundary beyond which nothing, not even light, can escape the pull of the black hole. It's hard to even begin to imagine what's happening inside a black hole, let alone inside a singularity. Inside the event horizon, the force of gravity is so intense that space and time themselves break down. Time slows as you approach the singularity, eventually coming to a complete halt at the very center. But gravity doesn't stop. It continues to pull everything inward, crushing matter and energy into an infinitely small point, where all the known laws of physics cease to apply. This is where gravity truly stops playing fair. The universe, which is normally so predictable, becomes completely unpredictable when gravity reaches its peak. The closer you get to the singularity, the more space itself is stretched and distorted. Imagine being inside the event horizon, where space is no longer a stable, consistent thing. Instead, it's a place where the rules we've come to trust, that things move in predictable paths, that time flows in one direction, are completely upended. Gravity bends space so much that the very fabric of the universe itself is pulled and warped, creating an environment so strange that we can barely make sense of it. This is what makes the singularity such a strange and fascinating concept. It's not just that the laws of physics no longer hold, it's that gravity has reached a point where it dominates everything. It's as if gravity is the ultimate force, the force that dictates how everything behaves. At the singularity, gravity wins, and everything else follows its lead. When we talk about black holes, we often focus on the event horizon, the boundary beyond which nothing can escape. But the singularity is where gravity reaches its ultimate strength. It's a place where space and time collapse into something we can't fully understand, a point where all the mass of the black hole is concentrated into an infinitesimally small area. This is where gravity becomes the ultimate power in the universe, and everything we know about the laws of physics falls apart. What does it mean for gravity to stop playing fair? It means that gravity, which is normally just a force of attraction, becomes a force that overwhelms everything. It becomes a force that bends the very fabric of space-time, a force that even light cannot escape. It means that time, which we usually think of as flowing in one direction, is twisted and distorted near the singularity. It means that space itself, the very stage upon which the universe unfolds, is warped beyond recognition. At the singularity, gravity doesn't just hold things together, it tears apart the very idea of what space and time are. The idea that you could have a point where all the mass of a star, for example, is crushed into a single point is mind-boggling. The fact that the gravity of that point is strong enough to pull everything toward it, even light, challenges everything we know about the universe. We've learned to understand gravity on a scale that affects everything from the smallest atoms to the largest galaxies. But at the singularity, gravity becomes so intense that it stops obeying the usual rules. It doesn't just pull, it pulls everything into itself, collapsing the universe into something we cannot even begin to imagine. This idea challenges us because it speaks to something deeper than just physics. It's not just that we don't understand what happens inside a black hole. It's that the very concept of the singularity forces us to confront the limits of our understanding. When gravity becomes so powerful that it warps space and time, it pushes us to the edge of what we can comprehend. It's a place where our theories stop working, where the language of physics breaks down and where everything we know about the universe is thrown into question. And yet, the singularity exists. It's not a theory or an abstract concept. It's a real phenomenon in the universe. We can't see it directly, of course, but we know it's there, hidden in the heart of every black hole. Its effects ripple through the universe in ways we can observe, from the way stars orbit around it to the way light bends and distorts as it passes near a black hole. Even though we can never get close enough to witness it firsthand, the singularity is there, quietly shaping the cosmos. As you lie there tonight, maybe staring at the dark ceiling or the quiet night outside your window, think for a moment about what it means for gravity to stop playing fair. It's a reminder that the universe is full of mysteries that are beyond our comprehension. Gravity, that force we rely on to keep us grounded, is also the force that shapes the entire cosmos. It pulls at us, it bends space, it warps time, and it creates singularities, places where the known laws of physics break down and where the universe stops making sense. But even in that confusion, there's something beautiful. The singularity reminds us that the universe is full of unanswered questions, full of places where our understanding falters, and even if we never fully understand what happens at the singularity, the quest to understand it pushes us forward. It challenges us to keep exploring, to keep asking questions, and to keep searching for answers, no matter how elusive they may be. In a way, the singularity is not just a point in space. It's a symbol of the mysteries that still await us, the frontiers that are yet to be explored. It's the universe's way of saying, you think you figured it all out? Well, there's always more to discover. And so, even as we come to the edge of our understanding, we press on, drawn forward by the pull of the singularity. It's a place where gravity stops playing fair, but it's also a place that challenges us to think bigger, to imagine further, and to explore the limits of our knowledge. When we think about space, we often think about a vast open expanse, a place of endless possibility where we can venture out and explore. There's always a sense of adventure in this notion, isn't there? The idea that the universe is a playground, and all we have to do is find our way to the next frontier, to the next discovery. But there is one place in the cosmos where this idea of exploration falls flat, where the very concept of journeying forward is rendered irrelevant: the event horizon of a black hole. The event horizon is the boundary, the point of no return that surrounds every black hole. It's the threshold beyond which nothing, not even light, can escape. And once you cross it, you're no longer just on a journey, you're headed toward an end, a place where space itself bends in on itself, and where even time starts to lose its meaning. The horizon you can never cross isn't just a physical boundary, it's a boundary of understanding, a place where the rules of the universe break down and leave us with more questions than answers. Imagine you're travelling in a spaceship, hurtling through the void at incredible speeds, and you approach a black hole. From a distance, it might seem like just another star or cloud of gas, but as you get closer, things begin to change. The stars around you start to warp, their light bending around the black hole as though being sucked in by an invisible force. The very fabric of space begins to stretch and curve, creating distortions in what you can see, what you can feel, and even in your sense of time. As you move closer to the event horizon, the pull of gravity becomes stronger, and time itself begins to slow. The closer you get, the more stretched out time becomes. It's like a rubber band being pulled taut, as if every second is being stretched out, turning from a moment into something much longer. But even as time slows down, you cannot escape the fact that the event horizon is waiting ahead of you. The point where, no matter how fast you travel, no matter how much you fight against it, you can never cross back. What makes the event horizon so fascinating is that it's not just a physical boundary. It's a point where our understanding of the universe begins to unravel. In the vast majority of cases, we experience time as something that flows forward, a river that carries us from one moment to the next. But inside the event horizon, this flow of time gets distorted. It's as though time itself becomes twisted, stretched, and ultimately frozen. To an outside observer, you would never actually cross the event horizon. You would slow down, get closer and closer, but never truly pass through. Instead, from the observer's perspective, you would simply fade away, as if your journey were suspended in time, unable to reach the end. This, in a way, is what makes the event horizon such a mysterious and haunting concept. It's a place where the laws of physics become unrecognizable. Inside this boundary, space itself behaves differently. The force of gravity is so intense that it warps everything around it. Objects are stretched and compressed as they approach the singularity, their very structure torn apart by the immense forces at play. And yet, no matter how far you go, you can never truly pass beyond the event horizon. It's an inescapable boundary, one that marks the point where the universe says, enough. Now imagine you're standing at the edge of this boundary, right on the cusp of the event horizon. You can't see it, it's invisible to the naked eye, but you can feel its pull. As you look out into space, everything around you begins to stretch. The stars blur into lines, and distant galaxies seem to distort as though being stretched by some unseen force. You're moving closer to the point where nothing can escape, and the very fabric of reality seems to bend around you. There is no turning back. This is where the mystery of the event horizon becomes so powerful. You're not just at the edge of the black hole, you're standing at the edge of our understanding. We don't know what happens inside the event horizon because, according to our current laws of physics, there is no way to see beyond it. Once something crosses the event horizon, it is lost to us, disappearing into the darkness, its fate sealed. And yet, Despite the fact that we can't directly observe what happens beyond the event horizon, there is something captivating about the idea that such a place exists. The very notion that there is a point in the universe where time and space stop obeying the usual rules is enough to fuel our imaginations. We know that the event horizon marks the edge of a black hole, but we still don't fully understand what happens beyond it. We know that the forces at work inside a black hole are beyond anything we've encountered before, but we can only guess at the details. It's a place of ultimate mystery, a place where reality itself may be rewritten. As you lie back, drifting off into the quiet, think for a moment about the event horizon. It's a boundary that can never be crossed, a place where the universe's rules break down and leave us with more questions than we can answer. It's a reminder that, for all our knowledge and exploration, there are still places in the cosmos that remain beyond our reach. The event horizon may be an invisible boundary, but it's one that reminds us of the vastness of the universe and the mysteries that lie just beyond our understanding. Perhaps that's what makes the event horizon so compelling. It's not just a physical boundary, it's a symbol of the unknown, a place where our curiosity and our limitations collide. It's a place that exists at the very edge of what we can comprehend, a reminder that there are still vast mysteries in the universe waiting to be uncovered. And even though we can never truly cross it, the event horizon continues to draw us in, challenging us to ask questions and seek answers, even when we know we may never fully understand the truth. In a way, the event horizon is a metaphor for all the boundaries in our own lives. There are always places we can't go, questions we can't answer, mysteries we can't solve. But that doesn't stop us from reaching for them, from trying to understand the things that are just beyond our grasp. And in that striving, in that search for answers, we find meaning. The event horizon may be a point of no return, but it is also a symbol of our endless curiosity, our desire to reach beyond the known, and our willingness to confront the mysteries of the universe, no matter how elusive they may be. So, as you rest tonight, think about the event horizon, that invisible boundary where time and space collide, where gravity stops playing fair, and where the universe itself seems to stretch and distort. It's a place we can never cross, but it's also a place that keeps us wondering, keeps us reaching, and keeps us questioning what lies just beyond the horizon. And perhaps, in the quiet of the night, that's all we really need, a reminder that there's always more to discover, always more to learn, even if we can never quite reach the edge. Light in many ways is the lifeblood of our understanding of the universe. It's how we see, how we explore, how we measure the distance between stars and galaxies. When we look up at the night sky, we are seeing light that has travelled across unimaginable distances, carrying with it information about the universe, from the colour of distant stars to the structure of faraway galaxies. Light, in its purest form, moves at the ultimate speed. Nothing in the universe can travel faster. But what happens when light itself is trapped, unable to escape from the very place it is most needed, the very place where the boundaries of space and time begin to collapse? What happens when light tries and fails to escape? This is the strange paradox of black holes, and more specifically the event horizon. The event horizon is a point of no return, a boundary beyond which nothing can escape the immense pull of the black hole's gravity, not even light. It might seem hard to believe, isn't it? Light, that uncatchable force that moves so fast it defies our usual ideas of time and space. Yet, when it reaches the event horizon, light is slowed, stretched, and ultimately trapped, and once light crosses that line, it's lost to the universe forever. To understand how this happens, we need to think about the way gravity works. Normally, gravity is something we're all familiar with. It's the force that pulls objects toward the Earth, keeps the planets in orbit, and holds galaxies together. The strength of gravity depends on two things: the mass of an object and the distance between objects. The larger the mass and the closer the objects are, the stronger the gravitational pull. But at the event horizon of a black hole, gravity becomes so intense, so overwhelming, that it warps space and time in ways we can't fully comprehend. Imagine standing near a black hole, looking at the event horizon. As you get closer, the light around you begins to behave differently. Light from distant stars is stretched, its wavelengths shifted to longer, redder frequencies. This effect, known as gravitational redshift, happens because the intense gravity of the black hole stretches out the light as it tries to escape. The closer the light gets to the event horizon, the more its wavelength is stretched, and eventually it is pulled into the black hole, unable to escape. This is where the real paradox begins. Light, the fastest thing in the universe, is now trapped by the very force that should, in theory, allow it to escape. If light can't escape, what hope is there for anything else? This is the essence of the black hole's power. It's not just that it pulls in objects and light, it pulls in everything, including the very fabric of time and space itself. The event horizon acts as a kind of one-way barrier. Anything that passes through it is drawn into the singularity at the center of the black hole, where gravity becomes so strong that it crushes everything into an infinitely small point. Once light crosses the event horizon, it's gone, forever. There's no way for it to turn back, no way for it to reverse its path and escape. It's a reminder of the incredible power of a black hole, the way it can bend the very laws of physics until they snap and form something entirely new. The question then becomes, why does this happen? What makes the event horizon so powerful that even light can't escape? The answer lies in the way that black holes bend space-time. You see, gravity doesn't just pull on objects, it pulls on space itself. The closer you get to a black hole, the more space itself is stretched and warped by its gravity. As space becomes increasingly distorted, the paths that light would normally travel along are no longer straight. Instead, they curve and bend, pulled inexorably toward the black hole's core. In this way, the event horizon is a point where space itself becomes so curved that even light can't find a way out. Imagine for a moment that you're standing in a deep well. The deeper you go, the more difficult it becomes to climb back out, until eventually the walls of the well become so steep and smooth that you can't climb at all. Light, in a sense, is like that. As it gets closer to the black hole, the walls of space-time curve inwards so steeply that it becomes impossible for the light to escape. No matter how fast it tries to move, it is pulled inward, caught by the black hole's gravity, and dragged toward the singularity. This is why black holes are often referred to as black. They don't emit light, nor can anything escape their gravitational grip. They are like cosmic prisons, where nothing, not even light, can break free. The vast majority of light in the universe, the light we see from stars and galaxies, can travel freely through space, bouncing off objects and making its way to our eyes. But near a black hole, this simple process is stopped in its tracks. Light can no longer follow its usual path. It becomes trapped in the gravity well, unable to reach beyond the event horizon. What makes this even more unsettling is that we can't directly observe what happens inside a black hole. Once light passes through the event horizon, it is gone, lost to the rest of the universe. We can never see what happens beyond that point. The information is trapped. It's as though the black hole itself acts as a barrier, not just to light, but to knowledge, to our understanding of the universe. This is one of the biggest mysteries of black holes. What happens to the information once it crosses the event horizon? Is it lost forever, or does it remain inside, hidden from view? This question remains one of the most important unsolved problems in modern physics. Yet, for all the strangeness and the mystery, the idea of light being trapped by a black hole is also profoundly fascinating. It forces us to confront the limits of our knowledge, to recognize that there are places in the universe where our understanding falters. We're used to thinking of light as the ultimate messenger, the thing that carries information across the cosmos. But at the event horizon of a black hole, light itself becomes the prisoner. It's a reminder that no matter how far we reach, no matter how much we understand, there will always be parts of the universe that remain beyond our grasp. In a way, the light that tries and fails to escape from a black hole becomes a symbol of the unknown. It represents all the mysteries we have yet to solve, all the questions that remain unanswered, and all the places where the laws of physics no longer apply. As you lie back tonight, perhaps staring up at the stars or reflecting on the quiet of the evening, think about that light. Think about the way it bends, stretches, and ultimately disappears as it nears the event horizon. It's a symbol of how little we truly know, how much more there is to discover, and how, in the vast expanse of the universe, there will always be things we cannot see, cannot understand, and cannot escape. Time, as we experience it, seems to move at a steady pace. It's a constant companion, one that shapes our daily routines and helps us organize our world. We wake up in the morning, make our way through the hours, and eventually fall asleep again. The days pass by, each one unfolding in a predictable rhythm. But what if time didn't behave that way? What if time could slow down, stretch out, or even come to a complete stop? This is the strange reality inside a black hole, where time itself behaves in ways we can barely imagine. In the vast majority of places in the universe, time moves as we expect it to. The clock ticks away, second by second, and we measure the passage of time with regularity. But near a black hole, something remarkable happens. As you get closer to the event horizon, the fabric of space and time becomes stretched, warped by the immense gravitational forces at play, and with it, time itself begins to slow down. Imagine you're standing on the edge of a black hole, looking out across the cosmos. You can see stars, galaxies, and nebulae, but everything around you seems to be moving more slowly than it should. The stars, which normally twinkle with their usual brightness, appear to flicker more faintly, their light stretched out. The galaxies seem to crawl across the sky, their motions sluggish and slow. From your vantage point near the event horizon, time is no longer a constant. It's bending, distorting, stretching in ways that are impossible to fully grasp. As you get even closer to the event horizon, something strange happens to your own experience of time. To you, everything might still seem normal. You're still moving through your day, still following the rhythm of your life. But to someone far away, someone standing far from the black hole, you are slowing down. To them, it would seem as if you are moving in slow motion, your every action stretched out across what feels like an eternity. The closer you get to the event horizon, the more time appears to stretch, until, at the very moment you reach the event horizon, time itself seems to come to a complete halt. This effect is known as time dilation, and it's one of the most mind-bending aspects of black holes. As you approach the event horizon, the warping of space-time becomes so extreme that the passage of time is slowed to a crawl. The closer you get, the slower time moves until, from the perspective of someone far away, you seem to freeze in place. And once you cross the event horizon, time as we know it no longer behaves in any predictable way. For all intents and purposes, from the perspective of an outside observer, it's as if you've become trapped in an eternal present, unable to move forward, unable to move backward. But for you inside the black hole, time doesn't appear to stop. You experience the passage of time just as you always have. Your own clock continues to tick at the same pace, second by second, but the rest of the universe is now moving at an increasingly rapid rate. To you, the stars and galaxies outside the event horizon seem to move faster and faster, their light flickering as though they are being accelerated through time. You're moving through time at your normal pace, but the universe outside is moving faster and faster. The further you move toward the center of the black hole, the more you become isolated from the rest of the universe, your personal experience of time standing in stark contrast to the time of everything else around you. This strange phenomenon leads to one of the most fascinating aspects of black holes. the notion that time, as we know it, becomes a relative experience. Time slows down as you approach the event horizon, and for an observer at a distance it seems to stand still altogether. But inside the black hole, time continues to pass normally, at least from your own perspective. The dissonance between the way time passes for the person near the black hole and the observer far away is a result of the warping of space-time, a fundamental feature of the intense gravitational fields around black holes. To understand this better, think about the way light behaves as it passes near a black hole. As light moves closer to the event horizon, its path is bent by the black hole's gravity. The closer the light gets, the more distorted its path becomes, and eventually, when it crosses the event horizon, it is trapped inside, unable to escape. Time behaves in much the same way. As you move closer to the black hole, time itself becomes bent and stretched. The closer you get, the slower time seems to move. Not just for you, but for everything around you. It's a reality where time and space become so distorted that they no longer operate as we normally think of them. It's not just the experience of time that changes either. The very concept of time itself is thrown into question. In the universe we live in, time flows in one direction, from the past through the present and into the future. But inside a black hole, where gravity is so extreme, time begins to behave differently. As you cross the event horizon, it's as if the normal rules no longer apply. Time stops being a simple, linear progression and instead becomes a more complex, entangled part of the fabric of space itself. In fact, the singularity at the center of the black hole represents a place where time and space themselves break down. Once you cross the event horizon, you're drawn inexorably toward the singularity, where the curvature of space-time becomes infinite. At the singularity, time ceases to have any meaning in the way we normally understand it. The closer you get, the more warped the concept of time becomes. Time is no longer a reliable, predictable force. It becomes something strange, something completely foreign to our experience of reality. It's a concept that challenges the very foundation of physics. In the world we know, time is something that moves forward, that keeps track of the events in our lives. It's something we can measure, something we can depend on. But inside a black hole, time becomes something else entirely. It becomes a fluid, ever-changing entity, distorted and twisted by the extreme forces at play. The further you travel into the black hole, the more time itself becomes an enigma. And yet, for all its strangeness, this bending and stretching of time offers us a deeper insight into the nature of reality. It shows us that time is not just a constant, unchanging force. It's not just a clock ticking away, ticking in one direction, marking off the seconds of our lives. Time is in fact a part of the very fabric of the universe, and as we explore more extreme environments like black holes, we see how deeply it can be affected by the forces around it. This revelation doesn't just change our understanding of time, it changes our understanding of the universe itself. Time is not a fixed, immovable thing. It is flexible, malleable, and tied to the very nature of space. In the presence of a black hole, where space itself is bent and warped, time follows suit. It's a lesson that challenges us to think about the universe in ways we never have before. So as you lie there, drifting into sleep, think about time, the way it moves, the way it bends, the way it shapes everything we know. Think about the black hole and how just beyond the event horizon, time becomes something completely different, something beyond our comprehension. It's a place where time slows, stretches, and ultimately stands still. It's a place that reminds us that time is not the unchanging force we often think it is. It's a part of the very fabric of the universe, shaped and stretched by the forces that govern everything around us. And even if we can never fully understand what happens to time inside a black hole, the mystery itself is enough to keep us wondering, to keep us searching for answers that may never come. The heart of a galaxy is often a place that we can't directly see. It's hidden behind layers of stars, nebulae, and cosmic dust, all swirling in the vastness of space. And yet, despite the distance and the obscurity, the heart of every galaxy is one of the most important and powerful features in the universe. It's at the center of this cosmic entity where we find some of the most mysterious objects in existence, supermassive black holes. These immense gravitational beasts are not just remnants of dying stars. They are the unseen engines that drive the growth and behavior of galaxies, including our own. They are the hidden hearts, the silent pulsing cores that hold everything together and govern the motions of the stars around them. At the center of our Milky Way galaxy, for example, lies a supermassive black hole named Sagittarius A. This black hole is about 4 million times the mass of our Sun, a staggering size by any measure. Yet, despite its immense mass, it's hidden from view. All we can see are the stars orbiting around it, swirling in tight circles, moving at incredible speeds. These stars are like cosmic dancers, caught in the pull of the black hole's gravity, unable to escape its grasp. But while we can't see the black hole directly, we know it's there. We know it's at the center of our galaxy, because we can observe the way these stars move, the way their orbits are influenced by an invisible force. The way the stars are pulled toward an unseen center is the key to understanding the nature of black holes. The speed of these stars and the way their paths curve around the galactic core can only be explained by the presence of a supermassive object, something with an overwhelming gravitational pull. That object, of course, is the black hole. It's strange to think about, isn't it? That at the heart of every galaxy, there lies something so massive, so powerful, that it can't even be seen directly. We know it's there because of the way it influences everything around it, but the object itself remains hidden. It's as if the black hole is the universe's great secret, a silent force that shapes the galaxy but refuses to reveal itself. And yet, this unseen force is essential for the galaxy's existence. The role of these supermassive black holes in the evolution of galaxies is still a topic of great interest for astronomers. One of the most fascinating aspects of black holes is how they seem to grow in tandem with the galaxies they inhabit. In the early stages of a galaxy's formation, the black hole at its center may start out small, but over time, as stars, gas, and other materials fall into it, the black hole grows larger and larger. This growth process is thought to play a crucial role in the way galaxies evolve. In fact, many scientists believe that the growth of supermassive black holes may be intimately connected to the formation of galaxies themselves. But while these black holes are important for the galaxy's development, they are also incredibly destructive. As matter falls into a black hole, it's heated to extreme temperatures, emitting radiation and creating jets of energy that shoot out into space. This process, called accretion, can cause enormous bursts of energy, often outshining the rest of the galaxy combined. The radiation from these black holes can also have a profound effect on the surrounding gas and dust, sometimes even preventing new stars from forming. It's a delicate balance. The black hole helps shape the galaxy, but it can also stifle the birth of new stars. The supermassive black hole at the heart of the Milky Way, like the ones in other galaxies, isn't just a passive object. It's a dynamic, active force, constantly interacting with its environment. It shapes the way the galaxy looks, dictates the motion of the stars around it, and influences the overall behavior of the galactic system. In many ways, the black hole is the engine that powers the galaxy, and without it, the galaxy might not exist as we know it. This hidden heart is also a reminder of the scale of the universe. We often think of our galaxy, the Milky Way, as just one of billions of galaxies in the universe, but in the grand scheme of things, it's just a tiny speck in the vastness of space. And yet, at the heart of it, there lies this incredible force, a force that shapes everything around it. The more we learn about black holes and their role in the universe, the more we realize how little we know about the true nature of the cosmos. But despite the mysteries and the challenges, the hidden heart of the galaxy remains a source of fascination. We may never fully understand the depths of these objects, but we can still marvel at the fact that they exist at all. The black hole at the centre of our galaxy, and the countless others scattered across the universe, serve as reminders of the vastness and complexity of the cosmos. They are the ultimate cosmic enigma, forces of nature that we can never fully comprehend but can't help but be drawn to. They are the hidden hearts that power the galaxies, and in many ways they represent the great unknown, the things we cannot see but know are there, shaping the universe in ways we will continue to explore for as long as we look up at the stars. As you settle into your thoughts tonight, perhaps take a moment to think about this hidden heart. Think about the supermassive black holes at the centre of every galaxy, their presence unseen yet undeniable, quietly shaping the universe. They are forces beyond our comprehension, forces that govern the very fabric of space and time. And though they remain hidden, they are an essential part of the cosmic dance, the forces that bind the universe together and ensure that the galaxies continue to evolve, grow, and change. In the stillness of the night, as you ponder the mysteries of the cosmos, remember that there are things in this universe that we may never fully understand. The hidden heart of every galaxy is one of those things. It's a force that shapes everything around it, even though it cannot be seen, even though it lies beyond our reach. And yet it is one of the most important forces in the universe, a reminder of the power and complexity of the cosmos. When we think about the universe, we often think of it as a place of growth, of expansion, of creation. Galaxies form, stars are born, and life finds its way on distant planets. But there is another side to the universe, a side that deals with endings, with the collapse of structures, the disintegration of stars, and the eventual breakdown of all things. This side is just as much part of the universe's story as its birth and growth. It's the side that shows us the true fragility of the cosmos, a place where everything eventually reaches a limit, where the laws of nature dictate that even the most stable systems will eventually collapse. And at the centre of this collapse, we find the language of the universe's greatest force, gravity. The concept of collapse in the universe is not just a theoretical one. We see it in action all around us, from the death of stars to the ultimate fate of entire galaxies. When a massive star runs out of fuel, it can no longer support its own weight. The core of the star collapses inward, and if the star is massive enough, this collapse continues until it forms a singularity, a point where gravity is so intense that nothing, not even light, can escape its pull. This is the birth of a black hole, one of the most extreme and fascinating objects in the universe. But the language of collapse isn't just about stars. It's about everything that happens when a system reaches its limit. When we look at a collapsing star, we're seeing the end of a long process, the final chapter in a star's life. Stars are born in vast clouds of gas and dust, and for millions of years they shine brightly, powered by the nuclear fusion in their cores. But eventually they run out of fuel. Without the energy from fusion, the outward pressure that holds the star up against the force of gravity begins to fade. The star begins to collapse inward, its outer layers falling toward the core, and this collapse releases an enormous amount of energy. In the case of supernovae, this explosion is so powerful that it can outshine an entire galaxy for a brief period. But even the brightest stars must eventually burn out. After a supernova explosion, what remains is often a dense core, a remnant of the star's former glory. If the star was massive enough, this core will continue collapsing, becoming a neutron star or, in the case of the most massive stars, a black hole. The point of collapse, the moment where the star's gravity becomes so intense that it cannot be resisted, is the moment when the universe speaks its most powerful language. It is a language of inevitability, of finality, of the collapse of one form of existence into another. The language of collapse tells us that no matter how grand the star, no matter how much energy it has expended over its lifetime, it will eventually succumb to the same forces that govern all things, gravity and entropy. This is the great irony of the universe. We live in a cosmos that is constantly expanding, where stars and galaxies are born, evolve and die. But the universe itself is a place where collapse is just as inevitable as growth. Every star that forms, every galaxy that spins, every planet that orbits its sun is moving toward a final moment of collapse. The collapse of a star, the collapse of a galaxy, and eventually the collapse of the entire universe. It's not just a matter of space, it's a matter of time. In the end, everything must return to a state of entropy, a state of disorder, where the collapse becomes the final word. And yet, collapse is not just the end. It's also the beginning of something new. When a star collapses, when it dies in a supernova, it releases a burst of energy and heavy elements into the surrounding space. These elements are the building blocks of new stars, new planets, and eventually new life. The collapse of one star is in a sense the birth of the next generation. Without collapse, there would be no new creation. It's a paradox. Destruction and creation are intertwined, inseparable, part of the same cosmic cycle. When we turn our attention to black holes, we see this paradox in its most extreme form. A black hole is the ultimate collapse, a point where gravity has become so intense that space itself is distorted beyond recognition. But even black holes have their role to play in the universe. They shape the formation of galaxies, they drive the motion of stars, and they act as the cosmic vacuum cleaners, pulling in matter and energy and redistributing them across the cosmos. The collapse of a star into a black hole is the end of that star's life, but it is also the beginning of a new phase in the life of the galaxy, as the black hole grows and influences everything around it. But the language of collapse goes beyond stars and black holes. It is the language of the universe itself. We see it in the death of galaxies, in the eventual fate of the universe as a whole. The universe, as we know, is expanding. Galaxies are moving farther apart, and the energy of the universe is spreading out, becoming more diffuse. But eventually this expansion will slow, and the universe will begin to collapse. The ultimate fate of the universe could be one of collapse, a big crunch, in which all matter is drawn back together under the force of gravity. This collapse would be the ultimate end, the moment when the universe reaches its final limit. It's a cycle, a language of life and death, expansion and contraction, creation and destruction, that plays out on the grandest scale. The language of collapse, then, is a fundamental aspect of the universe. It's not just about what happens when stars die or black holes form. It's about the very nature of existence itself. The universe is constantly evolving, constantly moving toward new forms, new states, but it's also moving toward an eventual collapse, an end that will be the ultimate conclusion to the cycle of cosmic creation. And this end is not something to fear. It is simply the next step in the journey, the next chapter in the story of the universe. It's a reminder that everything in the cosmos is connected, that every beginning leads to an end, and every end leads to a new beginning. As you drift off into sleep tonight, think about the language of collapse. Think about the stars and galaxies, about the black holes and supernovae, and how they all tell the same story. The story of a universe that is constantly evolving, constantly creating and destroying, always moving toward the next stage of its existence. In the quiet of the night, think about the collapse not as an end, but as part of the cosmic cycle, a language that speaks to the very nature of reality. And know that, even in the face of collapse, there is always the possibility of something new, something beautiful, and something grand waiting to emerge. There's something uniquely unsettling about the idea of falling. We've all had that sensation, haven't we? A sudden jolt in our stomach as we tumble through the air, weightless for a moment before the ground comes rushing up to meet us. Whether it's a drop from a great height or a sudden lurch in a roller coaster, the feeling of falling is something we experience as a loss of control. Our body is pulled downward by gravity, and no matter how much we try to fight it, We inevitably fall, pulled by forces greater than ourselves. We don't know exactly when we will stop or where we will end up. All we know is that we are heading towards something inevitable, something from which we cannot escape. But now, imagine something different. Imagine you are falling, but you're not really moving. Imagine that you're caught in a kind of suspended animation, a place where motion and stillness blur together, and the very act of falling seems to lose its meaning. This is the strange reality near the event horizon of a black hole, where the feeling of falling becomes distorted and stretched out, where gravity is so intense that it warps not just space, but time itself. Inside the event horizon of a black hole, falling becomes an entirely different experience. As you fall closer to the singularity, you feel the immense pull of gravity growing stronger and stronger, but it's not like any kind of falling you've ever known. You might expect to feel a rush, a sense of acceleration, but in fact, from your perspective, you would feel almost nothing. The closer you get to the singularity, the more the concept of time itself begins to warp. Here's where it gets strange. From the perspective of an outside observer, you would appear to slow down as you approach the event horizon. In fact, as you reach the edge, it would seem as though you were frozen in time, your descent coming to a halt. To anyone watching from a safe distance, it would look like you were falling forever, yet never quite reaching the point of no return. The closer you get to the event horizon, the more time stretches. To an outside observer, your descent would seem to take an infinite amount of time. You would be falling forever without ever truly reaching the point where you've crossed the event horizon. The time it would take for you to fall into the black hole, from their perspective, becomes infinite. But from your point of view, things are quite different. You wouldn't notice time slowing down at all. As you fall into the black hole, time would seem to pass normally for you. You would continue falling, moving toward the singularity, not realizing that the rest of the universe is moving at an increasingly faster rate. You might feel the stretching of space itself, your body being pulled apart by the extreme tidal forces, but in terms of time, it would feel as though everything was happening in the ordinary flow of events. You wouldn't feel the slowness. You wouldn't notice that you were suspended in an eternal moment. This paradoxical nature of falling into a black hole, where you appear to fall forever without moving, is one of the most fascinating aspects of the universe's deepest mysteries. It's the intersection of space, time, and gravity, where the normal rules of physics break down and become almost unrecognizable. The further you fall, the more the boundaries between movement and stillness fade. You're falling, but you aren't really moving. You're falling forever, but you're never really getting anywhere. The stretching of time and the sensation of being caught in a gravitational pull so powerful that it distorts your perception of movement is one of the most profound consequences of black holes. It's a reminder that space and time are not separate entities. They are part of the same fabric, one that can be bent, stretched, and torn by the immense forces at play. And when it comes to black holes, that fabric is stretched to its absolute limit. The more you fall toward the singularity, the more you enter a world where the very concepts of motion and time lose their meaning. This sensation of falling forever without moving is also tied to the broader implications of gravity itself. We often think of gravity as something that pulls objects toward one another, as a force that keeps us anchored to the earth. But near a black hole, gravity becomes something more. It becomes a force that warps not just the motion of objects, but the very passage of time. As you fall deeper into the black hole, you are pulled toward an infinite point of collapse, where the normal laws of physics cease to function as we know them. Time, space, and gravity all collapse into one singularity, one place where everything that we understand about the universe seems to break apart. And here's the thing, if you were to fall into a black hole, you would never be able to send a signal back to the outside world. Once you cross the event horizon, the point beyond which nothing can escape, you are cut off from the universe. No information can travel back to tell the tale. You are forever separated from everything you once knew. From the outside world, it would appear that you have fallen into nothingness, that you have disappeared into the black hole, as though you were never there at all. The information about your fall is lost, unable to escape. Your experience of falling is trapped in the black hole, and the rest of the universe is left to continue on without you. But from your own perspective, it's a different story. You are falling, but you're not moving. You are falling, but you're not reaching any destination. Your fall is eternal, but you're not truly going anywhere. It's as though you are caught in a moment of infinite time, a place where the normal flow of events breaks down, and where time itself is stretched beyond comprehension. Falling, but never truly arriving. Time seems to stand still, even though you're moving toward the singularity at the heart of the black hole, a point where all things collapse. The paradox of falling forever without moving is a reminder of just how strange and mysterious the universe can be. It's a place where our usual understanding of time and space is tested, a place where our everyday experience of reality no longer applies. When you fall into a black hole, the very nature of the universe is twisted, warped, and distorted. And yet, despite the bizarre nature of this experience, it is still a part of the cosmos, still governed by the same fundamental forces that shape the universe. So as you drift off into sleep tonight, imagine that feeling of falling forever without moving. Think about the black hole, the event horizon, and the paradoxes that emerge when gravity, time, and space collide. Think about the stretching of time, the bending of space, and the strange, unbreakable pull that draws everything into the black hole's heart. It's a reminder that the universe is full of mysteries, some of which we can barely begin to understand. But even in the face of these mysteries, we continue to look up, to wonder, to search for answers, knowing that just like the fall into a black hole, our quest for knowledge will never truly end. When we think of matter, we usually picture something solid, tangible, something that has substance and definition. Matter is what makes up everything we can see and touch. The chair you sit on, the air you breathe, the food you eat. It's what gives the universe its structure, its form. Matter follows the laws of physics and behaves predictably, at least within the conditions that we experience every day. But there are places in the universe where matter behaves in ways that are far beyond our usual understanding, where it loses its familiar form and identity. And one of those places is at the center of a black hole, inside the singularity, where matter forgets what it was and transforms into something we can't even begin to comprehend. This is the ultimate mystery of black holes. When matter is compressed so tightly, when it's subjected to the unimaginable forces of gravity, it seems to lose its very identity. At the singularity, the infinitely small point at the center of a black hole, the forces of gravity become so intense that they collapse all matter into a state where the usual rules no longer apply. There is no longer a clear distinction between different types of matter. At the singularity, everything, stars, planets, gas, even light, is crushed into a single point of infinite density. It's as though matter forgets what it once was and merges into something new, something we cannot fully understand. In the universe, matter comes in many forms. We have atoms made up of protons, neutrons, and electrons, which combine to form molecules, the building blocks of all the matter around us. These atoms are arranged in complex structures that give rise to the diverse range of substances we encounter: solids, liquids, gases, and everything in between. These substances have their own identities, their own properties, and they follow the laws of chemistry and physics that govern their behavior. But once matter is drawn into a black hole, once it crosses the event horizon, everything changes. As matter falls toward the singularity, it is stretched and compressed by the intense gravitational forces of the black hole. The closer it gets, the more it is distorted. Time slows, space bends, and the very fabric of reality seems to warp and stretch. And when matter reaches the singularity itself, it is no longer recognizable as the substance it once was. The atoms, the molecules, the particles that once made up the matter are no longer distinct. They're crushed into a single point, where the forces of gravity overwhelm every other force and where the laws of physics break down completely. This process is often referred to as spaghettification, because as matter approaches the black hole, the gravitational forces pull at it with such intensity that it stretches and elongates like a strand of spaghetti. This stretching happens because gravity is stronger the closer you are to the black hole. As the difference in gravitational forces between the parts of the object becomes greater, it causes the object to elongate and eventually be torn apart. For an object falling into a black hole, this is the ultimate fate. It is stretched and torn apart until it becomes indistinguishable from the black hole itself. But even this stretching is only the beginning of the transformation. As matter reaches the singularity, all the distinctions between different forms of matter vanish. The concept of matter itself breaks down. In the intense gravity of the singularity, the very particles that make up matter are crushed into an infinitesimal point. Matter forgets its identity, losing its familiar structure and form. It is no longer anything that we would recognize as matter in the usual sense. Instead, it becomes part of the singularity, part of the collapse that is happening at the heart of the black hole. This idea of matter forgetting what it was is both unsettling and awe-inspiring. It forces us to confront the limits of our understanding of the universe. Matter, the very stuff that makes up everything we know, can be so thoroughly changed by the forces of gravity that it becomes something else entirely. It's a reminder that the universe is not always predictable, that the rules we rely on to explain how the world works can break down in the most extreme environments, and yet even in this state of transformation, black holes remain vital to the ongoing evolution of the universe. While matter may lose its identity at the singularity, the process of collapse releases enormous amounts of energy and matter into the surrounding space. This energy can fuel the formation of new stars and galaxies. Black holes may destroy, but they also create. They play a key role in the cosmic cycle, where creation and destruction are intertwined, where the death of a star gives rise to the birth of new structures. The matter that forgets what it was inside the black hole may be lost to the universe, but it leaves behind a legacy in the form of new cosmic matter and energy. As you lie there, perhaps drifting towards sleep, imagine for a moment the strange process of transformation that occurs in the heart of a black hole. Picture the matter being drawn in, compressed, stretched, and ultimately forgotten as it is swallowed by the singularity. It's a reminder of the impermanence of all things, the way everything in the universe is subject to change, to collapse, to reinvention. Matter, as we know it, can be torn apart, reassembled, or even erased completely. But in the grand scheme of the cosmos, this process of transformation is a necessary part of the cosmic cycle. In the face of such extreme forces, it's easy to feel small, to feel like we are powerless in the face of the universe's most powerful phenomena, and yet, there is something profoundly humbling in the knowledge that we are all made of the same matter that stars are made of, that black holes feed on, that galaxies are composed of. We are all part of the same cosmic dance, from the smallest atom to the largest black hole. The matter that makes up our bodies, our world, our universe, is constantly changing, constantly transforming, but it is always part of something greater. The matter that forgets what it was inside a black hole is not truly lost. It is transformed, reconfigured, and repurposed as part of the universe's endless cycle of creation and destruction. Just as a star can collapse into a black hole can eventually evaporate, releasing its energy back into the cosmos, ready to fuel the creation of new stars, new galaxies, new forms of matter. In this way, the black hole becomes a cosmic recycler, turning the old into the new, transforming what was once one form of matter into another. So, as you think about the universe tonight, about the vastness and the mystery, Consider the strange and profound nature of black holes. Think about the way they reshape matter, how they force it to forget what it was, and how they play a role in the endless cycle of transformation that defines the universe. And in that contemplation, take comfort in the fact that even in the most extreme, incomprehensible places in the cosmos, the universe is constantly evolving, constantly changing, and constantly moving forward, just as we are, even when we don't always understand how or why. If you were to drift silently near the edge of a black hole just outside the event horizon, you would be floating at the boundary between two radically different worlds. Out here, space and time are still familiar, still something you can measure, still something that feels connected to the laws of physics we know. But just one step closer, past that invisible threshold, and you enter a region where gravity overwhelms everything. Yet even in this quiet, almost imperceptible boundary zone, something else stirs. Faint, elusive, and almost ghost-like. These are the quantum murmurs at the edge, whispers of a reality far stranger than the one we can see. Quantum mechanics and black holes are not easy companions. On one side, you have Einstein's theory of general relativity, which explains the grand, sweeping structure of space-time and gravity. On the other, you have quantum mechanics, the language of the tiny, the rules that govern particles, energy, and the chaotic dance of the subatomic world. Each of these theories works beautifully within its own domain. But when you try to put them together, when you take gravity and push it down into the quantum scale, at the very edges of a black hole, they clash in ways that defy understanding. And that's where the murmurs begin. Because at the edge of a black hole, in the region near the event horizon, quantum mechanics starts to make its presence known. The emptiness of space isn't truly empty. Instead, it's alive with fluctuations. Particles appearing and disappearing, brief sparks of existence that flare into being and then vanish just as quickly. We call this quantum foam, a restless sea of energy at the smallest scales of reality. Most of the time, this quantum activity is far too subtle for us to notice. But near the event horizon, where gravity presses space-time to its limits, these quantum effects begin to matter. One of the strangest and most fascinating consequences of these quantum whispers is something called Hawking radiation. Stephen Hawking proposed that black holes are not entirely black. They actually emit a faint, ghostly radiation caused by quantum effects near the event horizon. Here's how it works. In the quantum world, pairs of particles are constantly popping into existence, a particle and its antiparticle. Usually they annihilate each other almost immediately. But near the event horizon of a black hole, something strange can happen. One particle falls in, while the other escapes. From a distance, it looks as though the black hole has emitted a particle, as if it is slowly leaking energy into the universe. This is the first real sign that quantum mechanics has something to say about black holes. A soft murmur that suggests these cosmic giants may not be entirely eternal. Over unimaginable stretches of time, a black hole could slowly evaporate, bleeding away its energy through this faint radiation until it finally disappears. This is not something we will ever see with our own eyes. For a black hole the size of the ones we know, the time scale for this evaporation is so vast that it makes the lifetime of stars look like brief sparks. But it tells us something profound. Even at the very edge of the most extreme gravitational wells in the universe, the rules of the quantum world are still there, whispering their secrets. But the quantum murmurs at the edge are not just about Hawking radiation. They speak to something deeper. The conflict between the smooth, predictable fabric of space-time and the chaotic, probabilistic world of quantum physics. Near the event horizon, these two descriptions of reality are forced to overlap. Relativity tells us that the event horizon is a clean boundary, a point beyond which nothing escapes. Quantum physics, however, suggests that information, the fundamental instructions of the universe, might still linger, somehow encoded in the quantum structure of space-time itself. This is where one of the greatest puzzles in modern physics emerges, the black hole information paradox. According to quantum mechanics, information can never be destroyed. If you burn a piece of paper, you might turn it into ash and smoke, but in principle, every bit of information about its original state is still there, scrambled but not gone. But what happens if you throw that same piece of paper into a black hole? Classical relativity says it's gone forever, lost, no trace. But quantum mechanics says that can't be true, and so at the very edge of the black hole where quantum rules and gravitational rules collide, there is an unresolved tension, a whispering debate between the two deepest theories of physics. These quantum murmurs challenge our understanding of reality itself. They tell us that black holes are not just cosmic vacuums that swallow everything and hide it forever. They may in fact be something more complicated, something that holds secrets in a way we do not yet understand. Some scientists think the information might be smeared out across the event horizon, like a thin holographic film. Others believe that new physics, something we haven't yet discovered, must step in to resolve the paradox. And in those tiny fluctuations, those faint invisible whispers of quantum behaviour, may lie the key to understanding not just black holes, but the fundamental nature of the universe. It's a strange thought. The edge of a black hole, a place so violent and extreme that even light itself cannot escape, may be governed not only by gravity but by the tiniest quantum rules, the faintest possible shiver of the universe's smallest components. These are the murmurs at the edge, soft, nearly imperceptible, but powerful enough to challenge our deepest assumptions. And if you imagine yourself there, hovering just outside the event horizon, you might almost feel it, not in the literal sense but as a presence, the hum of space itself, the restless quantum foam flickering beneath the surface of reality, as though the universe is holding on to its deepest secrets in the tiniest possible motions. This is where the known world gives way to something new, where we are forced to admit that we do not yet have all the answers. The quantum murmurs at the edge are not just scientific curiosities, they are hints of the future. They are the first threads of a larger theory, one that might someday unify gravity and quantum mechanics into a single, elegant description of everything. For now, though, they remain whispers, teasing, elusive, just beyond our reach. They remind us that even in the darkest places in the universe where gravity reigns supreme, the smallest, quietest forces are still at work, writing the next chapter of the cosmic story. As you lie there tonight, perhaps half asleep, imagine those faint quantum ripples at the edge of the black hole. Imagine them not as noise, but as a kind of quiet music, a subtle rhythm playing at the boundary between what we know and what we don't. And know that in those whispers, those invisible flickers at the edge of the abyss, there may be an answer waiting, one that could rewrite our understanding of the universe itself. For most of our lives, information seems simple. You pick up a book, and the words are there. You write a letter, and the meaning endures. Even when things are destroyed, when you crumple that letter or burn the book, we tend to think of the information as gone, erased forever. But in the deepest layers of the universe, information is far more stubborn than that. According to quantum mechanics, information, the fundamental description of everything that exists, can never truly vanish. It can change shape, it can hide, it can be scrambled beyond recognition, but it cannot be erased. And this is precisely where the strange world of black holes creates one of the greatest puzzles in science. If information can never be destroyed, what happens when it falls into a black hole? A black hole, after all, is a one-way door. Matter crosses the event horizon, pulled in by a gravity so overwhelming that even light cannot escape. From the outside, nothing comes back. To us, it seems that whatever falls in is simply gone. And for a long time, that was exactly what physicists assumed, that black holes swallow everything whole, with no regard for the rules of quantum mechanics. But then the paradox emerged. If information is truly lost inside a black hole, it would violate one of the most basic principles of physics. And physics does not tolerate contradictions lightly. Stephen Hawking in the 1970s brought this paradox into the spotlight. His calculations suggested that black holes emit radiation, what we now call Hawking radiation, and that this radiation causes black holes to slowly evaporate over unimaginably long timescales. But here's the problem. This radiation is thermal, meaning it carries no information about the matter that originally fell into the black hole. If the black hole eventually evaporates completely, all the information it once contained seems to disappear with it. This conclusion shook the scientific world because it implied something impossible. The universe would lose information forever. But quantum mechanics insists that information cannot be erased. Not by time, not by destruction, not even by a black hole. And so began one of the longest, most heated debates in modern physics, a debate that continues to this day. Many physicists now believe that information isn't truly lost in a black hole. Instead, it might be stored in ways that are subtle and hidden from us, encoded in the fabric of space and time itself. Some suggest that the information is smeared across the event horizon, imprinted there like faint writing on an invisible surface, a concept known as the holographic principle. In this view, a black hole is like a cosmic vault, its event horizon acting as a two-dimensional surface that somehow contains every detail of what has ever fallen inside. This idea may sound bizarre, but it's grounded in serious physics. The holographic principle suggests that the universe itself might be like this, that the three-dimensional world we see is actually encoded on a distant two-dimensional boundary. Black holes, then, might not be exceptions to this rule, but proof of it. They may be the most extreme examples of how the universe preserves its information, no matter how strange or inaccessible it becomes. Other theories go even further. Some physicists propose that information doesn't stay on the event horizon, but is instead released in subtle ways, carried away by Hawking radiation, not as featureless thermal energy, but with faint quantum-level imprints of what once fell in. If this is true, then black holes are not information destroyers. They are information scramblers. They take everything that falls inside, matter, energy, and information, and transform it into something almost unrecognizable before slowly leaking it back out into the universe, scattered and encoded in ways that we have not yet learned to read. And yet, despite these theories, we still don't have a definitive answer. This is the essence of the black hole information paradox. We know that information must go somewhere, but we don't yet know how or where it's stored. It's as if the universe is speaking a language we don't fully understand, a language in which nothing is truly forgotten, but everything can be rewritten in a form so alien to us that it appears to be gone. Think of it this way. Imagine you wrote a letter and then shredded it into 1 billion microscopic pieces. To you, it might look as though the information is gone, but in principle, every piece still exists. And if someone, with infinite patience and infinite precision, could gather those pieces and put them back together, the message would be restored. A black hole may be doing something similar, shredding information until it's so thoroughly scrambled that it's unrecognizable, but never truly destroying it. And in this strange, almost poetic way, black holes become something more than cosmic monsters. They become libraries, silent, impenetrable libraries where every book has been torn apart and scattered, every word broken down to its smallest fragments, but nothing is ever truly lost. If this is true, it means that the universe is far more orderly than it seems. It means that beneath the chaos, beneath the collapse, beneath the crushing gravity of black holes, there is still a kind of hidden accounting system, a way for the universe to keep track of every particle, every quantum state, every shred of information that has ever existed, even if we can't yet read it. For now, all we can do is listen to the whispers of theory and math, to the hints left behind by quantum mechanics and relativity, to the faint suggestion that the universe has a memory far deeper and stranger than ours, and maybe, just maybe, black holes are the keepers of that memory, dark, silent archives at the edge of existence, guarding information that refuses to vanish. So, as you lie here and let your thoughts drift, consider this. In a universe where everything seems so fragile and fleeting, there may be no such thing as true loss. Even in the heart of a black hole, even at the singularity itself, the story of what once was may still be there, hidden in a form we do not yet understand, and waiting for the day when we finally learn how to read it. If you were to drift toward the event horizon of a black hole, most theories once suggested you wouldn't notice much at first. You'd pass that invisible boundary without a bump or a flash of light. No dramatic wall, no barrier. Space would simply continue to curve around you, and you'd move inward, unaware that you'd crossed the point of no return. But then came an idea that shattered this quiet picture, a controversial concept known as the firewall. The firewall is not a literal wall of fire, but the name captures its essence, a violent, unimaginable boundary of energy at the event horizon itself. If this idea is true, then the peaceful, uneventful crossing that general relativity predicts might be an illusion. Instead of gently slipping through the horizon, you would be annihilated instantly, burned into quantum nothingness by a wall of pure destructive energy. This proposal doesn't come from science fiction. It arises from one of the deepest paradoxes in modern physics, the clash between quantum mechanics and general relativity. On one side, Einstein's theory says that crossing the event horizon should be uneventful, a process physicists call the no-drama principle. On the other side, quantum mechanics insists that information can never be destroyed. And when these two rules collide, something has to give. The firewall is one possible outcome of that collision. To understand why this idea emerged, we have to go back to the black hole information paradox. If information can't be destroyed, and if Hawking radiation really carries away tiny bits of information over time, then the event horizon of a black hole must somehow keep track of that information. But there's a problem. If information is stored at the horizon and eventually radiated away, then anyone falling into the black hole should, in principle, be able to interact with that information. Quantum mechanics doesn't like that. The rules of quantum physics say that information can't be perfectly duplicated. It can't exist in two places at once, and this is where the firewall comes in. Some physicists suggested that to prevent this impossible duplication of information, something drastic has to happen at the event horizon. Instead of letting you pass smoothly through, the horizon itself might erupt with energy, destroying anything that tries to cross. The firewall would be a kind of cosmic enforcement mechanism, protecting the laws of quantum mechanics by violently erasing anything that reaches the horizon. It's a terrifying concept. If the firewall exists, then the event horizon of a black hole is not a gentle threshold at all. It is a wall of unimaginable energy, a final catastrophic boundary where matter, energy, and information are obliterated. In this view, there is no slow fall into the singularity, no timeless drift into the unknown. You would never make it that far. You would be unmade the instant you touch the horizon itself. But here's the problem. This idea, while dramatic, collides head-on with Einstein's theory of relativity. According to relativity, nothing special should happen at the horizon. Space-time there should feel smooth and continuous, even if you can never escape. The firewall turns this on its head, replacing the serene crossing with a violent physics-breaking explosion of quantum energy. And so the debate rages on. Some physicists argue that the firewall is an unavoidable consequence of quantum rules. Others insist that it's a mistake, a sign that we don't yet have the right theory to unify quantum mechanics and gravity. Perhaps, they argue, there is a deeper layer of physics that resolves the paradox without invoking something as extreme as a cosmic wall of fire. There are even alternative ideas like complementarity, which suggest that both views might be true. that from the perspective of an outside observer, information is stored at the horizon and radiated away, but from the perspective of someone falling in, the crossing is smooth and uneventful. In other words, reality might be different depending on who's looking. This is not just strange, it's unsettling. It forces us to confront the possibility that what happens at the edge of a black hole is not one single thing but two different realities layered over each other. And then there are those who believe that the answer might lie in something even stranger. Holography. If the universe is fundamentally holographic, if everything inside a black hole can be described as information encoded on its horizon, then there may be no need for a firewall at all. The information isn't lost, but it also doesn't require a catastrophic wall of energy to protect it. The horizon, in this view, is not a furnace. It's a boundary of information, silent and cold, yet holding everything that has ever fallen through it. But we don't know for sure, and that's what makes the firewall so haunting. It might exist, or it might not. It might be one of those ideas that gets replaced by a deeper, more elegant theory. Or it might be the grim truth, a sign that the edges of black holes are far more violent than we can possibly imagine. What makes this debate so fascinating is that it's not just about black holes, it's about the deepest structure of reality. It's about whether space and time are smooth and continuous, or whether they are stitched together by quantum bits of information that enforce the laws of physics in ways that feel brutal to us. The firewall question asks whether the universe is as calm and orderly as Einstein believed, or whether at its most extreme edges it becomes something harsher and stranger. For now, we are left with the uncertainty. No telescope can peer into the event horizon to settle the question. No experiment on Earth can reproduce the conditions near a black hole. All we can do is follow the mathematics, argue, debate, and wonder which of these visions of reality is close to the truth. As you lie here in the quiet of the night, imagine for a moment that invisible boundary, the event horizon, and ask yourself what might be waiting there. Is it the calm, smooth crossing that Einstein predicted, a quiet step into the unknown? Or is it the firewall, a wall of unrelenting energy that burns away anything that dares to touch it? Maybe it is neither. Maybe it is something stranger still, something no theory has yet imagined. In the end, the firewall is more than just a scientific argument. It is a reminder that we are still standing at the edge of knowledge, staring into a darkness that has yet to give up its secrets. And in that darkness, just beyond what we can see, the universe continues to hold its mysteries, waiting for us to learn how to ask the right questions. In science, paradoxes are not just problems, they are signposts. They point towards something we don't yet understand, something that lies beyond the borders of our current knowledge. And when it comes to black holes, there is one paradox that has consumed physicists for decades, a puzzle so deep that it has forced us to question our most fundamental ideas about space, time, and reality itself. It is simply called the black hole information paradox. On the surface, the problem sounds straightforward. Information, according to quantum mechanics, can never be destroyed. That rule is not negotiable. It is one of the bedrock principles of physics. No matter what happens to matter or energy, whether it burns, melts, or is crushed into unimaginable conditions, the information about its quantum state must, in some form, remain. You can rearrange it, you can hide it, but you cannot erase it. Now take that principle and place it next to a black hole. A black hole swallows everything. Matter, light, energy. Once something crosses the event horizon, it is gone from the universe as far as any observer is concerned. And if Stephen Hawking was right about Hawking radiation, the black hole will, over an incomprehensible span of time, evaporate completely. But if the black hole vanishes, where did all that information go? That's the paradox. If black holes destroy information, then the laws of quantum mechanics are wrong. If information survives, then we are missing a key part of how black holes actually work. Either way, one of our most successful scientific theories has to bend or break. For a long time, many scientists sided with Hawking. He argued that information is truly lost in black holes, that once something passes the event horizon, the details of its quantum state are erased forever. It was a clean, simple answer, but it came at a cost. It forced us to accept that quantum mechanics, one of the most rigorously tested frameworks in science, was incomplete. Many physicists, especially those who believed in the absolute reliability of quantum mechanics, refused to accept this. Over time, new ideas emerged, each one an attempt to untangle the paradox without destroying the foundations of physics. One of the most striking of these is the holographic principle. According to this idea, all the information that falls into a black hole isn't destroyed at all. Instead, it is somehow encoded on the event horizon, a two-dimensional surface that stores the data of everything that has ever crossed it. The interior of the black hole in this view is almost an illusion, a kind of three-dimensional projection created from information written on its boundary. This principle doesn't just apply to black holes. Some physicists argue that the entire universe may be holographic, that our three-dimensional world is a kind of projection from a two-dimensional information surface, far beyond what we can see. If that's true, then black holes aren't breaking the laws of physics, they're revealing them. Another approach comes from string theory, which suggests that the smallest building blocks of reality are not particles, but tiny vibrating strings. In this framework, black holes might not destroy information at all but transform it, scrambling it in ways we can't yet decode. Instead of being erased, the information is encrypted, still there, but hidden within the deep structure of space-time itself. Then there's the more radical firewall idea we considered earlier. This theory proposes that instead of gently crossing the event horizon, anything that reaches it is obliterated by a searing wall of energy. It's a drastic solution, but its proponents argue that it preserves quantum rules. If you're destroyed at the horizon, then no duplication of information occurs inside the black hole. The laws of physics stay intact, though at the cost of rewriting what we thought we knew about black holes entirely. And yet, there's another group of physicists who suspect we may be looking at the problem from the wrong angle altogether. Maybe there's a deeper theory, a true quantum gravity framework that unites relativity and quantum mechanics. In this view, black holes might not erase or even strictly store information. Instead, information might simply be woven into the very geometry of space-time in ways we can't yet perceive. The paradox would then dissolve not because we solved it, but because we finally learned the language the universe has been speaking all along. For now, no one knows which answer is correct. The paradox remains a stubborn, immovable riddle, but its persistence is part of what makes it so powerful. It forces us to confront questions that reach beyond black holes themselves. What is time? What is space? Is the universe fundamentally made of information? And are we even asking the right questions in the first place? And here's the most intriguing part. Every time we've wrestled with paradoxes in the past, they've led to breakthroughs. The ultraviolet catastrophe gave birth to quantum mechanics. The strange behavior of Mercury's orbit helped Einstein discover general relativity. Paradoxes are not dead ends, they are beginnings. The black hole information paradox might be exactly that, the doorway to a deeper understanding of reality. It may be the thread that, once pulled, unravels the old picture of the universe and reveals something entirely new beneath it. Imagine that for a moment. The universe as a kind of grand puzzle. Every law of nature a piece fitting neatly into place except for this one. This stubborn, unsettling piece that refuses to click. It sits there, mocking us, but at the same time it beckons. And every time we stare at it, every time we argue about it, we come a little closer to seeing the bigger picture. As you think about it, in the quiet, it's almost comforting. This paradox, this puzzle that frustrates the greatest minds in physics, is proof that there is still mystery in the universe. We haven't reached the end. We're still at the edge, peering into the darkness, asking questions that may take lifetimes to answer. And maybe that's the real beauty of it. The paradox that puzzles everyone is also the paradox that keeps us looking up at the stars, wondering what lies hidden at the heart of the cosmos, and daring to believe that one day we might finally understand. In the deep silence of space, black holes seem like the ultimate voids. They do not shine, they do not emit, they swallow everything that wanders too close. For a long time, it was easy to imagine them as perfect cosmic prisons, endlessly growing and never giving anything back. But in the 1970s, Stephen Hawking showed us something remarkable. Black holes are not entirely silent. They have a voice, faint and quiet, a whisper so soft it takes place over unimaginable spans of time. This whisper is known as Hawking radiation, and it changes everything we thought we knew about the darkness at the heart of the universe. To understand why Hawking radiation is so astonishing, we first need to revisit the strange rules of the quantum world. Even in what we think of as empty space, there is no such thing as true emptiness. Space is alive with fluctuations, a restless foam of energy where particles appear and vanish constantly. These virtual particles exist for only the briefest instant before they annihilate each other and return their borrowed energy to the vacuum. Normally, this activity is hidden, buried beneath the quiet fabric of space. But near the event horizon of a black hole, things change. The incredible gravitational pull of the black hole stretches and twists space-time so violently that these fleeting pairs of particles can be separated. One particle falls in, captured forever by the black hole's gravity, while the other escapes into the universe. To an outside observer, that escaping particle appears as radiation, emitted from the black hole itself. It's as if the black hole is slowly, almost reluctantly, leaking energy back into the cosmos. This process is unimaginably slow for the black holes we know. A black hole the mass of a star would take far longer than the current age of the universe to lose even a tiny fraction of its mass through Hawking radiation. But the principle is what matters. Black holes, once thought to be eternal, are not truly eternal at all. They fade, they evaporate. Over vast, unthinkable stretches of time, they shrink, their mass bleeding away in a faint glow until they vanish entirely. This quiet evaporation carries profound consequences. If black holes can disappear, what happens to everything they swallowed? Where does the information go? This is where Hawking radiation collides with the paradox we explored earlier. Hawking's original calculation suggested that the radiation is purely thermal, featureless, without any trace of the details of the matter that fell into the black hole. If that is true, then the information is simply gone, and that, of course, would violate one of the deepest principles of quantum mechanics. Information cannot be erased. So, if Hawking radiation is real, then it cannot be as simple as it first appeared. Many physicists now suspect that Hawking's radiation must in some subtle way carry information, not in a form we can currently understand, but hidden in tiny quantum correlations, encoded in ways so complex they are beyond our reach. If this is correct, then Hawking radiation isn't just a faint whisper of heat. It's a cosmic code, the black hole's way of slowly returning everything it ever consumed back into the universe, piece by piece, in an unrecognizable form. But even if we don't yet know how that code works, Hawking's insight changed black holes forever. They are no longer silent, eternal sinks of matter. They are dynamic objects, slowly interacting with the universe around them. And because of this, black holes may one day meet their end. Imagine the scene. A black hole that has existed for trillions upon trillions of years, long after all the stars have burned out. The universe is cold and empty, and the black hole, once a devourer of suns, has shrunk to a fraction of its original size. Its event horizon has drawn tighter and tighter, and its Hawking radiation has grown stronger as it shrinks. In its final moment, it will release a burst of energy, a last echo in the darkness, and then, for the first time in eons, it will vanish. That idea is almost poetic. black holes, which once seemed like eternal prisons, ultimately dissolve into the very universe they once fed upon. Even the darkest objects we know are not immune to time. They fade just like everything else. But Hawking radiation does more than give black holes an ending. It also ties them to the most fundamental questions about reality. If radiation carries information, then black holes become the ultimate test of how quantum mechanics and gravity fit together. If it does not, then our understanding of physics must change. Either way, Hawking's insight is not just about black holes. It's about the very structure of the universe. Even today, physicists are still unraveling what Hawking radiation means. Some believe it holds the key to unifying quantum theory and relativity, the two great pillars of physics that refuse to merge. Others see it as a clue that space-time itself is built out of quantum bits of information, a kind of cosmic fabric woven from the smallest threads imaginable. And still others think it might be pointing toward an even stranger reality, one in which black holes are not what we think they are at all, but windows into something deeper. For now, though, Hawking radiation remains a whisper, one we cannot hear directly, one that takes place over spans of time so great they make human history look like the blink of an eye. And yet, this whisper matters. It tells us that nothing is truly permanent. Not even the most powerful objects in the universe can escape the slow passage of cosmic time. And there is something strangely comforting in that, because if even black holes, the most terrifying, all-consuming phenomena in existence, are not eternal, then maybe nothing in the universe truly is. Everything changes, everything evolves, even the darkness itself. So as you rest tonight, imagine that faint glow, that quiet evaporation, those tiny echoes in the darkness. Picture a universe so vast and so patient that it can watch black holes slowly dissolve like mist. And remember that within those echoes lies one of the greatest mysteries of all. A mystery that might one day tell us not just how black holes die, but how the universe itself truly works. If black holes are the darkest objects in the universe, they are also the most patient. They do not burn out in the way that stars do, nor do they fade with the passage of cosmic ages as galaxies drift apart and dim. Instead, they linger, silent and immovable, holding their place in the universe for spans of time so vast they almost defy language. And yet, even these titans of gravity are not truly eternal. Their end comes, but it comes in a way so slow, so staggeringly drawn out, that it feels less like an ending and more like an eternal fade into nothingness. This is the story of an ending that takes longer than any mind can truly comprehend. The slow death of black holes through the whisper of Hawking radiation. To grasp just how immense these timescales are, imagine this. The universe today is roughly 13.8 billion years old. That number feels incomprehensible enough, but it is nothing compared to the lifespan of a black hole. A stellar mass black hole formed from the collapse of a massive star could take around 1067 years to evaporate through Hawking radiation. That is a 1 followed by 67 zeros, a number so large it stretches far beyond the lifespan of stars, galaxies, or even the structures of the universe as we know them. And supermassive black holes, like the one at the centre of our Milky Way, live even longer. Their lifetimes are measured not in trillions, not in quadrillions, but in numbers that dwarf anything we can write down without resorting to powers of 10. Long after every star in the cosmos has burned out, long after the last galaxies have gone dark, these black holes will still be there, drifting in an endless, silent night. For ages they will dominate a universe that has grown quiet and cold. The stars will be gone, the great cosmic furnaces extinguished, leaving behind only the embers of matter, white dwarfs slowly fading, neutron stars cooling to darkness, and isolated planets wandering without suns. In that dark era, black holes will remain as the final architects of gravity, the last massive objects left with any real power in the universe. But even they cannot hold on forever. Hawking radiation, faint and almost unnoticeable in the present age, will continue its slow work. Each quantum of radiation, each escaping particle, will chip away at the mass of the black hole. Slowly, silently, imperceptibly, these cosmic giants will begin to shrink. It will take longer than the lifetime of all the stars that have ever existed combined, but it will happen. The largest black holes, the ones that now anchor entire galaxies, will eventually begin to evaporate, one infinitesimal step at a time. And when that final stage comes, it will not be quiet. As a black hole nears the end of its life, it will begin to radiate faster. Its temperature will rise. What was once a slow, invisible trickle of Hawking radiation will turn into a flood of energy. The black hole will shrink more rapidly, its event horizon collapsing in on itself until, in its last fleeting moment, it releases one final burst of energy, a brilliant flash that marks the end of an object that has endured longer than anything else in the universe. But for most of its existence, that ending will be invisible. For eons upon eons, black holes will simply sit in the dark, slowly bleeding energy into space, like dying embers in a fire that never truly goes out until the very last instant. What's haunting about this picture is not just its scale, but its solitude. Imagine a future universe stripped of everything familiar. No stars, no galaxies, no light. Only black holes remain, scattered across an endless void, each one isolated, each one evaporating in silence, slowly unspooling itself back into the fabric of space-time. In that far-off future, time itself will feel almost meaningless, stretched so thin that change happens only in increments too small to see. And yet, there is something profoundly poetic about it. These black holes, once the most terrifying objects in the cosmos, become quiet ghosts. They no longer devour stars or anchor galaxies. They simply fade, vanishing bit by bit, their immense power dissolving into nothing. What happens after that? When the last black hole dies, what remains of the universe? Some physicists call this the heat death of the cosmos, a state where all usable energy has been spent, where everything has reached equilibrium, and nothing of interest happens anymore. It is the quietest possible ending, an eternal stillness where time stretches on, but change has effectively ceased. In this far-off future, black holes will be the last to go. They will be the final participants in the story of cosmic evolution, the last great actors to leave the stage. When they are gone, there will be no more structure left, no more gravitational anchors, no more brilliant eruptions of energy, no more events at all. Just an infinite, featureless expanse, the universe reduced to a thin haze of radiation, all of it too faint to give rise to anything new. And yet, even in that bleak vision, there's a strange kind of beauty. The end that takes eternities is not violent, it's not sudden, it is patient, it is quiet, it is the universe winding down not with a crash but with a sigh, an ending so gradual that if anyone were watching, they might never notice it at all. This vision of eternity forces us to think differently about time. We live our lives in hours and days, in decades and centuries, but black holes live in a different scale entirely. They stretch time out so far that our lifetimes, the whole lifetime of our species, of our planet, even of our galaxy, are nothing but brief sparks in their long, slow story. And yet, despite their scale, they remind us of something universal. Everything ends. Even the most immovable objects in the cosmos are subject to time. Even black holes, those seemingly eternal monuments to gravity, will one day fade away. They are a promise that nothing lasts forever, but also a reminder that in those vast stretches of time, the universe is still at work, still evolving, still transforming. As you lie here, imagine that slow, quiet future. Picture the black holes, the last remnants of a once bright universe, each one radiating faintly as it shrinks away. See them vanishing one by one, their final flashes echoing in a darkness so deep it has no bottom, and know that this too is part of the grand story of the cosmos, an ending that takes eternities, but an ending all the same. And perhaps that's not something to fear. Perhaps it is the ultimate expression of balance. The universe began in a burst of unimaginable energy, and one day it will settle into stillness, the fire spent, the stage cleared, and in that quiet, everything that was ever made will have had its time, its moment in the vast, sweeping arc of existence. Black holes, those mysterious titans of gravity, hold a strange place in the cosmos. They are both feared and revered, objects so powerful they swallow entire stars, and yet so enigmatic that their very nature continues to puzzle scientists. For much of their existence, black holes seem eternal, unchanging, silent sentinels in the vastness of space. But over unimaginable stretches of time, they begin to fade. Slowly at first, almost imperceptibly, and then with a quiet inevitability, these cosmic giants lose their grip on the universe and begin to disappear. This fading begins with the subtle, ghostly emission known as Hawking radiation, a quantum process predicted by Stephen Hawking that changed how we think about black holes forever. For years, black holes were thought to be absolute endpoints, cosmic cul-de-sacs where matter and energy disappeared without a trace. Hawking's work revealed a different story, that black holes are not completely black, but emit a faint glow, a trickle of particles escaping from their edges. At first, this glow is almost imperceptible. For black holes of stellar mass or larger, the rate of emission is so low that it takes timescales far beyond human comprehension for any significant mass to be lost. But as the black hole emits this radiation, it loses energy, and because mass and energy are equivalent, it slowly loses mass as well. This loss is tiny, but over cosmic epochs, it adds up. As the black hole shrinks, its temperature increases. Unlike most objects where bigger means hotter, black holes behave oppositely. The smaller the black hole, the hotter it gets. This counterintuitive behavior means that as a black hole fades, its emission grows stronger, accelerating the loss of mass. Eventually it reaches a point where the process becomes rapid, leading to a final, spectacular burst of radiation. But before that dramatic finale, the fading black hole goes through a long period of quiet decline. Imagine a star slowly dimming over millions or billions of years, but stretched out over incomprehensible scales. The black hole, once an all-consuming force, begins to soften its grip, releasing energy back into the universe in an almost ghostly manner. This process also carries profound implications for the information paradox. As black holes fade, they return energy, and possibly information, back to the universe. It raises deep questions about whether information swallowed by black holes is destroyed, or if it can somehow be recovered, perhaps encoded in the radiation emitted during this fading process. Some scientists have proposed that this fading phase might be the key to resolving the paradox. If information is carried away gradually by the Hawking radiation, then the black hole's slow fading isn't just the loss of mass, but a kind of cosmic recycling, a transformation rather than an erasure. The details are subtle, buried deep in the fabric of quantum physics, but the implications are enormous. Even as black holes fade, their influence on the universe persists. Their gravity shapes the motion of stars and galaxies, their emissions influence the formation of new stars, and their ultimate disappearance marks a profound moment in cosmic evolution. The fading black hole is not just a dying object, it is a vital part of the ongoing story of the universe. In contemplating this, it's natural to feel a sense of awe. The slow fade of a black hole connects the smallest scales of quantum physics with the grandest scales of cosmology. It reminds us that the universe is not static or eternal, but dynamic and ever-changing. Even the most seemingly permanent objects have a life cycle, a beginning and an end. So as you rest tonight, consider the fading black hole. Picture it as a cosmic ember, its once fierce blaze softened into a gentle glow, slowly cooling as it returns its energy to the vast expanse of space. Imagine the quiet transformation from darkness to light, from a force of destruction to a source of subtle energy. And in that vision, find a reflection of the universe itself, a cosmos in perpetual motion, where even the greatest mysteries are part of a continual cycle of birth, evolution, decay, and renewal. There is a question that has quietly followed scientists and philosophers for generations. What if everything we see, every star, every galaxy, every particle, every moment in time, is not separate and scattered, but part of a single, unified thing? What if, in a sense, the universe itself is one vast singularity, stretched and unfolded into the cosmic stage we inhabit today? When we talk about singularities, we usually imagine them at the heart of black holes, infinitely dense points where space and time fold in on themselves, where gravity overwhelms every other force and the normal rules of physics stop working. But some scientists have dared to take this idea further. They've asked whether the universe itself, at its very beginning, might have been a singularity. And if that's true, then maybe, in some deeper sense, it still is. According to the standard model of cosmology, the universe began about 13.8 billion years ago in what we call the Big Bang. But the term bang is misleading. There was no explosion in space. Space itself expanded from an unimaginably small, hot, dense state. A state that, when pushed to its limits, looks suspiciously like the conditions we describe as a singularity. In that moment, all the matter, all the energy, and even the very fabric of space-time were compressed into a single point without size, before erupting outward and evolving into the cosmos we see today. If that's true, then in some ways, we're all still living inside the aftermath of a singularity. Space didn't expand into something else. It created itself, stretching outward, carrying galaxies with it like seeds scattered in an infinite field. Every star, every planet, every black hole is part of that same unfolding process. The universe may look vast and separate, but at its root it may be the expression of a single, unified whole. Some physicists take this idea even further. They argue that the singularities inside black holes and the singularity that began the universe may not be entirely separate concepts. In fact, they may be linked by laws of physics that we do not yet understand. There are even theories suggesting that black holes could be gateways, not just to destruction, but to creation. Some models propose that inside every black hole, a new universe could be born, budding off from ours like a branch from a tree. If so, our own universe could be the offspring of another, formed in the singularity of some long-dead parent cosmos. If that sounds strange, it's because it is. But the mathematics does not dismiss it outright. The idea that a singularity could be both an end and a beginning is not just poetic. It may be embedded in the very structure of the universe. And then there is the question of what this means for our understanding of time. If the universe is, in some way, a singularity that has simply expanded, then time itself might not be what we think it is. From the perspective of the universe as a whole, there may be no true before or after, no linear sequence of moments the way we experience them. Instead, time may be another dimension of this singularity, something woven into it, inseparable from space and matter. In that sense, everything, the birth of stars, the death of galaxies, even our own brief lives, could be part of a single, timeless whole. From our limited view, we see change, motion, and sequence, but from a higher perspective, perhaps it all exists at once, contained in the singular fabric of the universe. This line of thought leads to a fascinating question. If the universe is one big singularity, are we inside it, or are we part of it? The difference might be purely semantic, because if space, time, matter, and energy are all facets of the same underlying entity, then we are not merely living in the universe, we are pieces of it, threads woven into the larger whole. We are not separate from the singularity, we are expressions of it. The more we study the cosmos, the more hints we find that support this interconnected view. Quantum physics shows us that particles can be entangled across vast distances, behaving as though they are part of the same unified system. General relativity reveals that space and time are inseparable, forming a single fabric. And black holes remind us that when you push the laws of physics to their limits, everything collapses into a single point. Perhaps this is the universe's way of whispering its true nature. It was one singularity, and in some way, it still is. This perspective changes how we think about everything. Instead of seeing black holes as isolated monsters and the Big Bang as a distant one-time event, we can see them as reflections of the same underlying reality. Singularities are not just strange exceptions to the rules of the cosmos. They might be the foundation upon which the rules themselves are built. Imagine for a moment what that means. It means that the universe is not just a collection of separate parts, but a single, vast entity. It means that the singularity at its beginning was not erased when the universe expanded, but unfolded, its essence still present in every corner of space. Every galaxy, every atom, every thought we have might be part of the lingering echo of that one indivisible point. And if that's true, then perhaps the end of the universe will be no different from its beginning. Many theories predict that the cosmos will eventually run out of usable energy, sliding into heat death, an endless state of stillness and cold. But there are other possibilities. Perhaps the universe will reverse its expansion, collapsing back in on itself, returning to the singularity from which it came. If that happens, then everything, all of space and time, every star and planet, every memory and moment will be drawn back together, merged into a single point, ready to begin again. And if that cycle is real, if the universe oscillates between singularity and expansion, then what we're seeing now may only be one chapter in a story with no beginning and no end. As you drift deeper into thought, imagine that. The universe as one vast singularity, not destroyed or reborn, but endlessly transforming. The same force that gave rise to everything still exists in every corner of reality, shaping it quietly, invisibly. Perhaps, in the deeper sense, the singularity never ended at all. It only changed shape, and we are living inside it. When we think of the universe, we usually imagine it as a one-way story. It has a beginning, the Big Bang, and one day it will have an end. Maybe it will fade into heat death, an endless dark where nothing new ever happens. Maybe it will collapse back into itself in a catastrophic big crunch. Or maybe it will tear itself apart in a big rip, with every galaxy, every atom, and every particle pulled away into nothingness. These are the endings we've been taught to picture. But what if the end isn't really an end at all? What if the universe has a way of starting over? This is the strange possibility of a cosmic reboot, the idea that the universe may not be a single, linear story, but a repeating cycle of births and deaths. That beyond every collapse, beyond every singularity, there might be a new beginning waiting to unfold. To understand this, we have to go back to what we know about singularities. A singularity is a point where space and time break down, where all of the universe's matter and energy are compressed into an infinitely small point. We see singularities at the center of black holes, and we believe one marked the beginning of everything, the Big Bang. But if a singularity could exist at the start of the universe, what's to stop one from existing at its end? And if such a singularity does form, why couldn't it explode outward again, creating another universe just as ours was born from one? This is the foundation of one of the most fascinating ideas in cosmology, the cyclic universe. In this model, the universe doesn't have a true beginning or end. Instead, it's locked in an eternal rhythm. It expands, it evolves, it collapses, and then it begins again. Every cycle erases what came before it, replacing it with something new. In a way, this idea is comforting. It suggests that even when the cosmos reaches its end, it isn't truly over. Instead, everything is folded back into a singularity, a cosmic reset point, and then bursts outward in a new Big Bang, starting another chapter in an endless story. Of course, no one knows what a rebooted universe would look like. Would it be identical to ours, playing out the same events over and over, like an infinite loop? Or would each new universe be different, reshuffled like a deck of cosmic cards, creating entirely new laws of physics, new galaxies, new stars, and new lives that would never even resemble what came before? There are even bolder theories. Some physicists suggest that our universe could be just one branch of a larger multiverse, with new universes budding off like leaves from an eternal tree. In this view, a collapsing universe doesn't simply reset. It gives birth to something entirely new, separate and self-contained, while our own universe fades into the background of an ever-growing cosmic forest. What makes this even stranger is that black holes might play a role in this process. There are speculative ideas suggesting that every black hole in our universe could be a kind of seed, a gateway to a new universe. Inside each singularity, space and time might pinch off and create a fresh reality, disconnected from ours. If that's true, then our universe itself might be the child of a black hole in another universe, and every black hole we see in our sky could be nurturing new universes of their own, each with its own physics, its own galaxies, and perhaps even its own versions of beings who look up and wonder the same things we do. If this sounds overwhelming, that's because it is. We're used to thinking of the universe as everything, but if cosmic reboots are real, then everything might only be one small chapter in an endless recursive story. And yet, there's something deeply human in the way this idea resonates. We live our lives within cycles. Days turn to nights, seasons shift, generations come and go. The universe itself might simply be doing the same thing, only on a scale so vast that we can barely comprehend it. Even if we never witness a cosmic reboot, even if our universe drifts into heat, death, and silence long before such a thing happens, the possibility itself is powerful. It suggests that endings are not what they seem. They are transformations. The universe doesn't stop. It changes its shape, discarding what it was and becoming something new. And maybe that means that everything we know, everything we experience, is just one part of a much larger story that has been playing out forever. A story of singularities collapsing and exploding, of realities beginning and ending, not once, but endlessly. As you let that thought settle, imagine it. The universe as a grand cycle, not bound to a single lifetime, but breathing in and out across eternity. Black holes collapsing into singularities, singularities blossoming into new universes, time itself folding and unfolding without a true beginning or end. If that's true, then we're not just inhabitants of one universe. We are part of an eternal chain of universes, each one born from the ashes of the one before. We are fragments of a story that never stops being told, and in that vision there is no final darkness, no ultimate silence, only the quiet before the next beginning. There is a point, somewhere far beyond the last galaxies, beyond the last faint traces of light, where the universe becomes almost impossibly still. It is a place of unimaginable distance and unimaginable time, where expansion has stretched space so far and so thin that everything familiar is gone. No stars, no planets, no heat, only a quiet expanse in which even the memory of motion seems to fade. This is where we might imagine what it means to rest at the edge of infinity. By this stage in the life of the cosmos, black holes have long since completed their slow fade. Their hawking radiation has evaporated them into nothing, leaving behind only faint ghosts of energy scattered across an almost empty universe. Galaxies have drifted so far apart that no observer could ever see another, even if one still existed to look. Space itself has expanded until it is cold and silent. Time, for all practical purposes, has lost its meaning. Infinity, it turns out, is not loud or violent. It is quiet. In this stillness, the fundamental forces of nature no longer compete in the ways we once knew. Gravity, once the architect of galaxies and the sculptor of stars, has done its work. It has pulled matter together, shaped it, destroyed it, and in the end, watched it fade. What remains now is not a universe of structures, but a universe of simplicity, a thin, stretched canvas of near-perfect emptiness. And yet, even here, something profound lingers. To rest at the edge of infinity is not simply to witness the end of things. It is to stand in a place where the story of the universe is unfolded in full. Every star that burned, every black hole that consumed, every moment of collapse and creation has already played out. What's left is the silence after the symphony, the quiet stillness after the last note has faded. But there is a strange beauty in that silence. Think about it. From the moment of the Big Bang, the universe has been restless. Matter rushed outward. Stars formed and died. Black holes grew and vanished. Energy flowed, transformed and dissipated. And through it all, gravity and time worked hand in hand, carving out the structure of everything we know. To reach the edge of infinity is to arrive at the moment when this restlessness finally ends. No more growth, no more collapse, no more change, only equilibrium, an infinite pause. Some physicists describe this final state as heat death, a universe in which all energy is evenly distributed, where no differences remain to drive motion or life or structure. It is a quiet, perfect balance. But others see it differently. They imagine that even at the edge of infinity, quantum fluctuations, the faint hum of the quantum world, may still stir in the emptiness. Tiny sparks of possibility, too small to disrupt the silence, but reminders that even in the stillness the universe is never truly dead. Could those faint whispers be the seeds of something new? Could they one day lead to another beginning, a new burst of expansion, another universe blooming out of the calm? We don't know, and maybe we never will. But in a way it doesn't matter, because to rest at the edge of infinity is not to ask what comes next. It is simply to exist in the vastness, to witness the universe not as it was, or as it will be, but as it is when everything that could ever happen has already happened. And perhaps this is what makes the concept of infinity so powerful. It is not just about endless time or endless space. It is about stillness. It is about the moment when the universe has stretched itself as far as it can go and simply stops changing. It is a kind of cosmic rest, not in defeat, but in completion. Imagine it for a moment. A universe without motion, without the rise and fall of stars, without the endless pull of gravity. A universe where there is no before or after, only a vast, unbroken present that extends forever. This is not a place we can travel to. It is not something we can ever witness. But in the quiet of thought, we can almost feel it. An infinite horizon, endlessly still, and in that stillness, perhaps there is peace. As strange as it sounds, this is the destination of everything. The stars, the galaxies, the black holes, and even the smallest particles of matter. All of it leads here to the infinite quiet. And if there is anything beyond that silence, a reboot, a new universe, or something stranger still, it will begin from this place of absolute rest, as if the cosmos itself must pause between each breath. So, as you lie there tonight, imagine that infinite horizon, the ultimate calm after the endless motion of cosmic history. Picture it not as an ending to be feared, but as the most profound stillness imaginable, the resting edge of all things, where time, space, and matter no longer rush forward but simply exist, together in unbroken quiet. Perhaps this is what it means to stand at the edge of infinity, to finally see the universe not in its motion, but in its stillness, and to find, in that silence, a kind of completion that no beginning or ending could ever truly offer. There comes a moment after every question has been asked and every possibility imagined, when all that remains is quiet. The universe, once roaring with the birth of stars and the collapse of giants, eventually softens into something else, a vast, unbroken calm. And as we drift toward that horizon, the one we cannot cross but can always feel, there is a sense that we are not falling into darkness, but floating into a silence that has always been waiting for us. This is the gentle drift beyond the horizon. For so long, we have looked at black holes as the ultimate boundaries, cosmic walls that separate what we can know from what we cannot. They are places where time slows until it almost stops, where gravity bends the universe into impossible shapes, where matter and information are twisted into something unrecognizable. And yet, at the heart of every black hole, and at the heart of the universe itself, there is something more than collapse. There is a strange and quiet kind of order. Imagine this drift not as an ending, but as a movement toward simplicity. All the chaos of the universe, the stars being born, the galaxies colliding, the endless dance of matter and energy, fades into a single, unified whole. Every event, every moment, every particle is drawn inward, back toward the point from which everything began. The singularity is not destruction, it is a return. Perhaps this is why the universe feels so impossibly vast to us. It is not just space, it is a story, and the story is written in arcs that stretch farther than our minds can follow. From the Big Bang to the first galaxies, from the birth of stars to the rise of black holes, and then to this, the quiet drift that comes at the end of it all, where gravity has had its final word and time has lost its urgency. And yet, as the universe drifts toward this horizon, there is no sense of violence. There is no shattering finale, no cosmic explosion tearing the fabric of everything apart. Instead, it is like a tide receding, carrying the last traces of light and heat with it. A slow fade into something deeper than stillness. Physicists call it the heat death of the universe, a state of perfect balance where no energy flows, no new stars are born, and no black holes remain to anchor the darkness. But perhaps that description is too cold, too clinical for what it might truly be. Because there is also a kind of elegance in this ending. It is not the death of the universe so much as its final rest. The stage is cleared, the lights dim, and all that remains is the quiet after everything has played its part. And in that quiet, there might be something else. Maybe in that infinite calm the universe does not stay still forever. Maybe from that emptiness a spark emerges, a fluctuation in the quantum foam, a ripple at the very base of reality, enough to set everything into motion again. Another beginning, hidden inside an ending. Another singularity, not as a collapse, but as a seed. If that happens, if the universe is truly cyclical, rebooting itself across incomprehensible stretches of time, then this gentle drift is not the final chapter at all. It is a pause, a deep breath before the next act. But even if there is no next act, even if this is truly the last horizon, it is not something to fear. Because in this final stillness, nothing is lost. Everything that ever was, every star that burned, every world that spun, every thought that lived and vanished, has already been written into the fabric of the universe. Nothing can erase that, not even the silence at the end of time. And perhaps that is why the idea of a gentle drift feels so comforting. It is not an ending with a sharp edge. It is the soft closing of a book after the last page has been read. You know the story now. You have seen it all. And even though the words no longer turn, the story itself will always remain. So as you rest here, at the edge of the cosmic horizon, imagine this quiet drift. Not a fall, not a plunge, but a surrender into stillness. Imagine the universe slowing, its motion stretching thinner and thinner until there is nothing left but the vast, endless calm of infinity. And if you listen closely enough, in that silence, you might almost hear it. The last echo of gravity, the final hum of time, fading not into darkness, but into something so still and complete that there is no difference between beginning and end, only a horizon that has been waiting for all things to return. And maybe, in that return, there is peace. And now, we've reached the quiet part of the story. From the first spark of the Big Bang to the slow fade of black holes, from the strange whispers of quantum physics to the stillness at the edge of infinity, we've followed the universe to its very limits. And in the end, what we found isn't fear, it isn't chaos, it's a kind of silence, a calm so deep that it feels almost familiar, like the steady rhythm of your own breath as you rest. The singularity, the horizon, the infinite. They're not just places in space, they're reminders that everything in the universe, every galaxy, every black hole, every fleeting moment is part of a single story. A story that may never truly end. So, as you drift off, let yourself feel small but not lost. You're made of the same matter that was born in the hearts of stars, the same fabric that once lived at the very beginning of time. You've always been part of this story. You always will be. And maybe that's enough. So close your eyes. Let the vastness of it all fade into the background. There is no rush here, no urgency. Just the quiet hum of a universe that has been unfolding for billions of years and will keep unfolding long after this moment has passed. And if you find this peaceful, if the stillness helps you rest, you can stay here as long as you like. Good night, traveller, and welcome to the horizon.